Right. Good afternoon, everyone. Welcome to the class. We have discussed the number systems. We have done with the number systems. Yes, good afternoon, everyone. Vamshi Krishna, can you say the question? Just elaborate what is the question? Question number 12 means. Right. I think everything is fine, audible, and video is fine. Now, most of you might have solved questions from classroom practice questions. Yeah, someone was asking about 12th question. Let me read the question. My PDF editor was not functioning properly, was not able to make a slide of this CRPQ, classroom practice questions. I think everyone is having those questions. Someone was asking about 12th question. A number capital N is stored in a 4-bit 2's complement representation as A3, A2, A1, A0. It is copied into a 6-bit register, and after a few operations, the final bit representation, final bit pattern is A3, A3, A2, A1, A0, 1. The value of the bit pattern in 2's complement representation is given in terms of the original number N is as. I hope everyone is having questions. Not audible? Is it clear? Yes. Yes, yes, yes. Right. Okay. No need to reply. Right. So, right. Did you get questions, sir? There is classroom practice questions, sir. You might have observed you got a PDF. Yes. Indra Kumar Verma, you did not, you might not have checked. Please check. Many are saying yes, sir. Some people are saying no. What is the reason for that? Yeah, you will get that hard copy. That is, material is there. We say volume 1. You will get material with classroom practice questions. Every chapter and there will be some questions. Okay. Okay. Try to get those PDFs. I will discuss all those questions. Let me make a slide of each and every question. I will discuss. Some people are saying no means if you don't have question papers, even though I read, may not be understanding what is that. So please try to get those PDFs. If not, please inquire. Everyone must get that PDF classroom practice questions of each and every chapter. Not the material, you will be getting questions, not with the solutions. Solution will be discussed in the class. That's the reason these are named as classroom practice questions. Right? Again, Shubham Kumar, I mentioned that you will get the hard copy once you come to the institute. There it will be provided a material, that is theory part, every chapter, and there will be questions. Purna Chandra, what happened? Yes. Toy yes, I do. Wait. So for now, I'm discussing these classroom practice questions of number systems. Everyone should get questions. Let me check if there is any problem. I think they might have mailed you all the questions. Every time they are doing that, some are already they have means. You need to check your mails. Please check. You will be getting, and I'll make a slide of each and every question also. I will discuss all the questions. No need to worry about classroom practice questions of number systems. I'll discuss. Fine. Now, as I discussed already, codes and code properties, I will discuss in combinational circuits. No need to worry about codes now. I will discuss those codes and code properties later. So until that, hold on. Now, next topic is Boolean algebra. After that extension, we do logic gates also. What is this Boolean algebra? Why we must know Boolean algebra? What is the base for this Boolean algebra? Why it is helpful? How it is helpful in our digital circuit design? We see all these, right? Yes, Arpit, I'll discuss. No need to worry. People are saying that it is there in the portal, CRPQ. Yeah, Ganeshwari, I do that. Every question I'll discuss, no need to worry. Please, right, I'll give you time to ask doubts. Until that, please wait. That's what I've been saying. Attagara Meti, Pranita. I do all those, don't worry. Please wait. Every individual's doubt, I'll clarify, and coverage will be 100%. No need to worry about coverage. That's what I've been saying. You will get all the clarity. Maybe, Madhusudan, please stop sending queries. Please let me proceed. All that right queries will be cleared at the end. Please wait. Right? Yeah, try Surya Teja. Try one more or some more. I will help you if you require any help from my side. Do that, please. Right? Okay. And is there any reason for joining later? Many are joining a bit later today. Right. XS3 codes, every code will be discussed in combinational circuits. I said, don't worry. Now you are worrying about that. What is that? Sai, Banawat Sai. I will discuss all the codes later. Network issue, is it? Okay. Fine. Now, let us see what is Boolean algebra. A special algebra for digital circuit design proposed by George Boole based on switching theory. I will discuss switching theory soon. Until that, hold on. So, based on switching theory, it is proposed a special algebra by George Boole. It is named as Boolean algebra. Base for this Boolean algebra is switching theory based on three functions, three logic functions: logical OR, logical AND, logical inversion. Based on these three functions, it is proposed a special algebra, which we name it as a Boolean algebra. So all these are based on switching theory. What is switching theory also? I'm going to discuss until that, hold on. So Boolean algebra is proposed by George Boole for digital circuit design based on switching theory. Base for this Boolean algebra is three basic functions, which are logical OR, logical AND, logical inversion. On ones and zeros. On ones and zeros. What are these three functions? Let us see first. Later we see what is the rules of this algebra. special algebra, Boolean algebra. So first, what are these three functions on ones and zeros? Which functions are logical OR, logical AND, logical inversion? Let us see one by one. Logical OR, which we represent with plus symbol. Then 0 logical or 0 is 0. 0 logical or 1 is 1. 1 logical or 0 is 1. 1 logical or 1 is also 1. It is not addition. It is logically OR function. 1 logical or 1 is also 1. Don't add these. If you're adding, you may be getting that 1 plus 1 is 2. 2 is nothing but 1 is carry, 0 is sum. You may be writing result is 0, which is sum. No, it is not addition. It is not addition. What is the proof for this switching theory? I'll discuss that later. Until that, hold on. So just accept this for now. I will discuss what is the proof of this logical OR function using switching theory later. Now, logical OR function, which is defined on ones and zero, the OR function we are representing with plus, it is not addition. 0 logical or 0 is 0. 0 logical or 1 is 1. 1 logical or 0 is 1. 1 logical or 1 is also 1. This is a logical OR function on ones and zeros based on switching theory. The next one is a logical AND. Let us see logical AND on ones and zeros. Logical AND. We use a dot symbol for representing AND function. 0 and 0 is 0. 0 and 1 is also 0. 1 and 0 is 0. 1 and 1 is 1. It is a logical AND function. 1 and 1. The dot is indicating AND function. Right? So 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. That is a logical AND function. Next, logical inversion. Logical inversion. Another name for this is a NOT function. We represent with apostrophe or bar. To represent inversion or NOT function, we use either apostrophe or bar. So what is it here is inverse of 0 is 1. Inverse of 1 is 0. 0 complement is 1. 1 complement is 0. Inverse of 0 is 1. Inverse of 1 is 0. That is a logical inversion or NOT function. Based on these three functions, it is proposed a set of rules for digital circuit design. Based on these three functions, which are functions? Logical OR, logical AND, logical inversion. Based on these three basic functions, it is proposed a set of rules which are called Boolean rules or Boolean axioms or Boolean postulates. Boolean postulates. Let us see what is this Boolean algebra rules. Before that, let me discuss a word in Boolean algebra, which is dual of a function. Dual of a function. It is dual of a function. How to get dual of a Boolean function specified? It may be expressed, the expression, you need to get dual of that expression. How to get dual of a function? Replacing logical OR with logical AND vice versa. In the given, if there is a logic 0, that 0 is replaced with 1. Logical OR is replaced with logical AND vice versa. Logic 0 is replaced with logic 1 and vice versa. This is a dual of a function. Why we are discussing dual here is you can understand soon. So while writing Boolean axioms, we are using this duality property. What is the property of duality is? Note. What is it here? If a function is true, dual of that function is also true. We don't need to verify. What is it here? If a function is true, then the dual of that function is also true. if you verify a function is true, if you write dual of that, you don't need to verify, it will be true. That is a principle of duality. What is it here? First thing is how to get dual of a function is to get dual of a given function or given expression, replacing logical or with logical and vice versa, replacing logic 0 with logic 1 and vice versa. That is the way we get dual of a function. And why we are discussing dual here is if a function is true, dual of that function is also true, we don't need to verify. We don't need to verify. Then we see what is the rules of this Boolean algebra, which are Boolean rules. Which are Boolean rules. Let us see what is that. Right. A logical OR with 0 is equals to A. What is the proof of this? The A can get either 0 or 1. You can verify by substituting possibilities. What are the possibilities? A is a variable, can have 0 or 1. 0 logical or 0 is 0. 1 logical or 0 is 1. So whatever you are giving on A will be the resultant. So A logical or 0 is A. What is dual of this? A logical OR is replaced with logical AND. 0 is replaced with 1 is equals to, what do we have right side? A, there is no OR, there is no AND, there is no zeros, there is no ones. So what is dual of this? See, A itself. A and 1 is equals to A. Is that true? Yes. 0 and 1 is 0, 1 and 1 is 1. That means whatever you are giving on A is resultant. A and 1 is A. So once you are verifying here, if you are writing dual, it will be true. We don't need to verify. That's what we have observed in duality. That here, if you are verifying here, if you are writing dual of this correctly, you don't need to verify. It will be true. It will be true. Next, A logical OR with 1 is equals to A logical OR with 1. A logical OR with 1 is equals to 1. How do you verify that? A can be 0 or 1. A can be 0 or 1. What is that here? 0 logical OR with 1 in 1. If A is 1, 1 logical OR 1 is also 1. So A may be 0 or 1. All possibilities. The resultant is 1 only. Irrespective of A, resultant is 1. When A logical OR with 1, it is equals to 1. What is dual of this? A logical OR is replaced with logical and 1 is replaced with 0 is equals to, what about RHS side? 1 is there, we are writing 0. While writing dual, 1 is replaced with 0, 0 is replaced with 1. Yes, A logical OR with 1 is 1, then dual of that is A logical OR is replaced with logical and 1 is replaced with 0. What is the right side we have? 1, that is equals to 0 when writing dual. Now, A logical OR with A is equals to A. A logical OR with A is equals to A. You can substitute either 0 or 1. Neeraj Meshram. Wait. You can replace with A bar also, not a problem. Right? Right? When you are ORing with 0, X, logical OR with 0 is X. Means that X can be any function. Not only A bar, you can write that A plus B bar also. Will it be a problem? Neeraj Meshram. Already I observed your question, did not reply, right? Because you are going to understand soon. Then again you are writing the question. That means if I keep on observing everyone's questions, right? Please wait. Follow, right? Follow. Then if you have doubts, I will discuss in question hour, right? Please, right? A logical OR with A is equals to A. How can we verify that? A can be 0 or 1. 0 logical or 0 is what? 0. 1 logical or 1 is also 1. A can be 0 or 1. You can verify. 0 logical or 0 is 0. 1 logical or 1 is 1. So resultant is A itself. What is dual of this? A logical or is replaced with logical and A is equals to, what is RHS? A itself. Dual. Now, A logical or with A bar is equals to A logical or with A bar, or A bar logical or with A. What can be the resultant? 0 logical or with 0 bar. What is 0 bar? 1. 0 logical or 1 is 1. A can be 1. 1 logical or with 1 bar. What is 1 bar? 0. Then 1 logical or 0 is also 1. So A can be either 0 or 1. Resultant is what? 1. I hope no doubt in that. What is dual of this? A logical or is replaced with logical and here it is A bar is equals to 1 is replaced with 0. A and A bar is equals to 0. Yes, correct. 1 and 0 is 0. 0 and 1 is also 0. A can be 0 or 1. A and A bar is 0. A plus A bar is 1. A and A bar is 0. I hope everyone is following. Now, A bar whole bar is equals to A. Correct. A bar whole bar is equals to A. 0 complement is 1, 1 complement is 0. That means again we are getting 0. 1 complement is 0, 0 complement is 1. Again it is 1. So A bar whole bar is equals to A. A bar whole bar is equals to A. What is dual of this? What is dual of LHS? Same. What is dual of this? Same. That means dual is also same. Such functions are called self-dual functions. So you can make a note here. When can we say a function is self-dual? If dual of a function is itself, then the function is called self-dual function. I will address this in detail after some more time, because we are going to address how many self-dual functions are possible for n variable also. How many functions, how many self-dual functions, how many self-complement functions, all these I will address soon. Until that point, at this moment we are addressing a word self-dual. What is self-dual? If dual of a function is itself, that means same, then the function is called self-dual function. So even though you are writing dual, it is getting same. Now, A logical or with B is equals to B logical or with A. A logical or B is equals to B logical or with A. What is this here? Commutative law. What is dual of this? A and B is equals to B and A. A and B is equals to B and A. And R is replaced with and, again R is replaced with and. So it is a commutative law. Purna Chandra. Wait for question hour. Right. So this commutative law, A logical or B is equals to B logical or A. Dual of that is A and B is equals to B and A. A logical or with B logical or with C is equals to A logical or B logical or with C. What is this? Associative law. It is associative law. Then A and dual I am writing B and C is equals to A and B and with C. A and B and with C. What is this here? Associative. Associative with respect to R, associative with respect to and. Associative law. With respect to Boolean algebra also we have associative, right? So commutative, associative. Now, A and with B logical or with C is equals to A and B logical or with A and C. What is this distributive law? What is here? A and with B logical or with C is equals to A and B or with A and C. It is a distributive law. So this function is distributed among these. So A and B or with A and C. What is the dual of this? A logical and is replaced with logical, or B logical or C is replaced with B and C. Is equals to, what is dual of this RHS? A and B. A or B. Right? R means and A and C. A logical or with C. A plus BC is equals to A plus B and with A plus C. Distributive law. Observe this correctly. A and with B plus C is equals to A and B plus A and C. Similarly, what is dual of this LHS? And is replaced with R is replaced with and. A plus BC is equals to, now A and B, A plus B, A and C, A plus C, R is replaced with and. That is dual. A plus BC equals to A plus B and A plus C. A plus C. Distributive law. Right? With respect to R, with respect to and, it is distributive. A logical or with A and B is equals to A logical or with A and B. What kind of resultant? If I take A common, one logical or B. What is one logical or B? 1. So A and 1, resultant is what? A. Check it correctly. Right. So the resultant is A. What is dual of this? A and with A logical or B is equals to, what is that? Again, A. A plus AB is equals to A. Now A and A plus B is also A. Dual of this, A or is replaced with and B, A plus B is equals to, what about RHS? A itself. Is a itself. Now A logical or with A bar B is equals to A logical or with A bar B is equals to, right? Already we know that A plus BC is equals to A plus B and A plus C, distributive law. Am I right? A plus BC equals to A plus B and A plus C. Now, what we can write? A plus A bar B is equals to, what we can write? A plus A bar and with A plus B. A plus A bar is what? 1. And with A plus B. Resultant is what? A plus B. Resultant is A plus B. Observe correctly. Distributive law I am applying here. A plus BC equals to A plus B and A plus C. So in place of A plus BC, what we are writing? A plus A bar B. If you are applying distributive law, A plus A bar and with A plus B. A plus A bar is 1, and with A plus B is A plus B. What is here? A plus B. Right. Right, dual of this. What is that? A logical or is replaced with logical and A bar and B, A bar plus B is equals to what we have in RHS, A plus B. Dual of that is A and B. Dual of that is A and B. A and with A bar plus B is equals to A and B. A and B. Now, I'm moving to next slide. Now, A plus B whole bar is equals to A bar dot B bar. What is this, sir? De Morgan's law. What is dual of this? A and B whole bar is equals to A bar plus B. Dual. A plus B whole bar replaced with dual A and B whole bar. So A bar and B bar, A bar plus B bar. A plus B plus C whole bar is equals to A bar dot B bar dot C bar. Now A and B and C whole bar is equals to what we get here? A bar plus B bar plus C bar. A bar plus B bar plus C bar. Now that is De Morgan's law. AB plus A bar C plus BC is equals to AB plus A bar C plus BC is equals to AB plus A bar C. What is this? Consensus law. I'm going to give you a proof for this. Hold on. AB plus A bar C plus BC is equals to AB plus A bar C. People may be struggling. How can I remember this equation? No, remember, I'll give you another way of analyzing this. So you don't need to remember specifically like this only. So you can observe where is the possibility of eliminating a term that I'll discuss soon. Hold on. In next itself. Let me complete a dual of this, then we see that. So what is this here? Consensus law. So what is dual of this? A plus B and with A bar plus C and with B plus C is equals to A plus B and with A bar plus C. A bar plus C. Dual I'm writing. AB, A plus B. A bar and C, A bar plus C. B, C, B plus C. These are odd, these are AND. Right? What about RHS? A and B, A plus B. A bar and C, A bar plus C. Odd and dual. Right? It is a consensus law. So first AB plus A bar C plus BC. Now this BC can be ANDed with 1. Will it change the function? No. BC can be ANDed with 1. It won't be changing the function. The one I can write it as A bar plus A. The one I can write it as A bar plus A. A bar plus A. If BC is ANDed with 1, no change in that. The one if I write A bar plus C also, no change in that. Now AB plus A bar C plus A bar BC plus ABC plus ABC. Then what I can do, in these two, if I take AB common, one logical or C. In these two, if I take A bar C common, one logical or B. Right? So one logical or C is 1. One logical or B is also 1. So AB and with 1 is AB. A bar and C and with 1 is also A bar C. That is a resultant. AB plus A bar C. AB plus A bar C. Observe correctly what I have done. AB plus A bar C plus BC. The BC we can AND with 1. The one I can written as A bar plus A. Then if you are expanding that, finally in these two if I take AB common, one logical or C. And in these two if I take A bar C common, one logical or B. So one logical or C is 1, one logical or B is also 1. So AB plus A bar C is there. So AB plus A bar C plus BC is equals to what we are writing? AB plus A bar C. AB plus A bar C. Right? See, how can we understand this consensus law? How do we need to observe this consensus law? How do we eliminate the term which is extra? Right? So without that also functionality will be same, means why should I use that term? Right? So observe correctly. Follow what I've been mentioning. Here A bar. In these two terms, what you are observing? A variable is existing in complementary and uncomplementary form. A uncomplementary, A bar is complementary form. A bar are ANDed with the B and C. Two more variables. A and B, A bar and C. So A and A bar are ANDed with two variables B and C. What is third term? BC, B and C. So third term is AND of these two. Check it correctly. What is it here? AB plus A bar C. In this A bar are complementary and complementary variable. These two variables are ANDed with two more variables B and C. What is third term? AND of those two variables. Without this also, functionality will be same. When you are observing A bar in two different terms and observe these two variables, and if you are ANDing these two, we are getting third term, then this third term is extra, unnecessary, redundant. All this terminology we are going to learn. What is here? This B and C is becoming third term, it is becoming redundant. So A bar are ANDed with B and C. The third term is B and C. This third term is becoming extra. Right? I will elaborate this a bit more. Right? Now, AB. AB plus B bar C plus AC is equals to. Simple thing. What is it here? B is there, B bar is there. B bar are ANDed with A and C. Third term is AC. This is now extra. Then what we get? AB plus A bar C. AB plus A bar C. Which one should be eliminated? Should be observed correctly. AB plus B bar C plus AC. As we have B and B bar in these two terms. So we need to observe remaining. What is it? A, C is there. So third term is AC only. So without this AC, functionality will be same. AB plus B bar C plus AC is equals to AB plus A bar C. Now, next. Plus BC is equals to AB plus AC bar plus BC is equals to. What can we observe here? C is there, C bar is there. These two are ANDed with A and B. This term is AB extra now. So AC bar plus BC is the result. Don't expect consensus law must be given AB plus A bar C plus BC equals to AB plus A bar C only. They may be giving anyway. So you must be in a position to answer correctly. Or you must be in a position to apply this consensus law. Second one. Oh, sorry. By mistake I have written. This B1. Right. Some of you have observed, right? It is B bar, right? Right. Now, C bar are ANDed with A and B. The third term is A and B. This is extra. Without this functionality, same means AC bar plus BC. AC bar plus BC. Right. Now, so this is consensus law. This is consensus law. This is also consensus law. Instead of all these, let me make a generalized. What is that here? A F1 function F1. It can be anything F1 plus A bar F2 plus what again should I write? F1 and F2. F1 and F2 is equals to A F1 plus A bar F2. Right? It's not only A. You can use that like a P F1 plus P bar F2. P and P bar also may be functions. Plus F1 and F2 is equals to P F1 plus P bar F2. P may be another function. P may not be a variable. So resultant is what? P F1 plus P bar F2. Applying consensus law. Applying consensus law. Is that clear? Mostly we have been getting questions, simple questions on consensus law. Or it is helping us in saving time sometimes. In analysis or minimization, it becomes easy once you are applying consensus law. So remember, observe correctly, understand correctly about this consensus law. Right? That is a consensus law. Moving to next slide. Let us discuss some more things here. While defining function, what are you writing here? F of a comma b comma c. Correct? While defining a function, you are saying it is f of a comma b comma c. This a, b, c are called variables of function. Am I right? These a, b, c's are called variables of function. F of a comma b comma c. F of a comma b comma c. A, b, c are called variables of function. While writing expression for the function, what we are using? A bar, B, B bar, C, C bar. We are using A bar, B bar, C bar also. These are called, what is it? Literals of function. No need to worry. I'll give you clarity about this, right? So, while expressing function, we are specifying variables of the function. While writing expression, we are using literals. What do you mean by this? Variable can exist in only one form, but literals can exist in both complementary and uncomplementary variables. Variables can exist in only one form. Literals can exist in both complementary and uncomplimentary form. Or to get clarity, what we can say with respect to variables, A and A bar are one variables, same. With respect to variables, A and A bar are same. With respect to literals, A is separator, A bar is separator. With respect to literals, A is separator, A bar is separator. With respect to variables, A and A bar are representing only one variable. While counting number of variables, you should not count A and A bar separately. A and A bar are representing only one variable with respect to variables. While counting variables, you should not treat A is separate, A bar is separate. A and A bar are only one variable. While counting literals, you need to count A separately, A bar separately. While counting literals, you should count A is one literal, A bar is another literal. With respect to literals, A is separator, A bar is separator. With respect to variables, A and A bar are same. A and A bar are same with respect to variables. But with respect to literals, A is separator, A bar is separator. So, variables can be only one form. Literals can exist in both complementary and uncomplementary form. Why we are discussing this here, you may understand soon. Let's hold on. So variables and literals. I may be using frequently this terminology, right? So not only me, in the competitive exams, they have been asking questions like find variable count in the minimal expression, find literal count in the minimal expression. This type of questions also they have been asking. Or while framing theory questions like ESC, they may be saying like this. In minimization, variables can be eliminated. In minimization, literals can be eliminated. In this minimization, right, the number of variables or number of literals they may be mentioning. So about minimization, about Boolean expression, you must be clear with this terminology also. What is that here? Variables and literals. Variables can exist in only one form. Literals can exist in both complementary and uncomplementary. While counting variables, A and A bar must be treated as one variable. While counting literals, you should count A separately, A bar separately. Now, let us see one more important thing. If I say A plus B bar C is the function, A plus B bar and C is the function. What is the complement of this? How do you get that? Complement of this F. If it is F is a function, if I want to get F bar, what we can do? A plus B bar C whole bar is equals to what you can write? A bar and B bar C whole bar. And again, what we do? A bar and with the B bar whole bar plus C bar. And what we get here? A bar and with the B plus C bar. This is what we can say complement of function specified. If a number of hierarchical levels in the given function more, then you need to have more number of steps. Understand once again? If a number of hierarchical levels in the given function is more, then number of steps required to get complement of your function is also more. Instead of this, I can use only 2 steps to get complement of a function, irrespective of complexity of given function. Irrespective of complexity of given function, I can complete a complement of a function in 2 steps using De Morgan's principle. Using De Morgan's principle, we can write complement of a function in 2 steps. What is the De Morgan principle? How can we apply the De Morgan's principle to get complement of a function? Let us see with example. First, what is the 2 steps of De Morgan's principle to get complement of a function? The first rule is dual of given function. Second step is complement each literal. This is a procedure to get the complement of a given function using De Morgan's principle. What we discussed, first step is what? Writing dual of given function. Second step is complementing each literal. Complementing each literal. Let us see what is it. Given function is what? A plus B bar and C. A plus B bar and C. What is first step? Writing dual. How to write dual? Replacing or with and with or. Replacing or with and with or. Then what we can do here? So logical or, logical and. Which one should be replaced first? The important thing I'm addressing now, remember this. When we have a function like this, in this given we have a logical or as well as logical and. You need to write dual. While writing dual, or must be replaced with and must be replaced with or. Right? So in these, which one should be replaced first? Again, we should go with priority. It is not from left to right or right to left in the expression. What should I use? Priority must be used. When we have logical or, logical and, first priority goes to logical and, next priority goes to logical or. In the given function, while writing dual of that function, in the given function we have logical or, logical and. In that case, the first priority goes to logical and, then logical or. So in this logical or is there, logical and is there. First we need to write dual of and function. What is it here? B bar and C is a B bar plus C. Dual I have it. B bar and C is dual is B bar logical or with C. This B bar C is logical or with A, then and with. That is first step. That is first step. Then what is second step? Complementing each literal. Then what is it here? A is replaced with A bar, B bar is replaced with B, C is replaced with C bar. Complementing each literal. What is here? If it is uncomplimentary, make it complementary. If it is already complementary, make it uncomplimentary. Complementing each literal. A plus B bar and C is the given function. We want to get complement of that function. In that first step is writing dual. Second step is complementing each literal. First step is writing dual. Second step is complementing each literal. That's what we have done. But while writing dual, if you have a logical or logical and in the given function, priority goes to logical and then logical or. Then logical or. So when we have logical or logical and in the given function, priority goes to and then logical or. Next. Let me take one more. If this is a given function, how to get complement of this? If this is given function, we need to write dual, then complementing each literal to get complement of a function using De Morgan's principle. In that first step is what? Writing dual. While writing dual, what we are observing? Logical or, logical and logical or. Priority goes to, don't say logical and. Because this is in the parenthesis, brackets. Now, highest priority goes to brackets or parenthesis. Understand point correctly? When we have logical or logical and, priority goes to logical and. When we have logical or logical and also brackets, which is parenthesis, then highest priority goes to parenthesis. Whatever is there in the parenthesis, that will be getting highest priority, then logical and then logical or. Point should be understood correctly. So priority goes to now parenthesis or brackets, then logical and then logical or. So in the given function, what we are observing? Or and there is a bracket or parenthesis. Now highest priority goes to parenthesis, then logical and then logical or. So C plus D bar is there in the parenthesis. So what is dual of this? C and D bar. Is logical and with B. It is a logical or with B. Is logical or with B. This entire is a logical or with A bar. That is logical and with B bar. What we have done? First, priority for parenthesis. Then logical and logical or. This is logical or with A bar. This must be logical and with A bar. Anyone is having any doubt in this? Simple. Parenthesis is getting highest priority. So in parenthesis, what we have? Let me write once again. Right. Here, A bar plus B and with C plus D bar. We need to write dual of this. For that, you need to observe the priority. First of all, we need to observe what are the functions we have. Logical or, logical and also parenthesis. Now, highest priority goes to parenthesis, next logical and next logical or. So in the parenthesis, what I can say, C plus D bar is there. We need to write dual of this, nothing but C and D bar. This term which is there in the parenthesis is logically ANDed with B, then logical OR with B. This entire term is logical OR with A bar. This entire term must be logical and with A bar. Right? What is this? Writing dual. That is first step. That is first step. What is second step? Complementing each literal. A bar is replaced with A, B bar plus C bar D. Right? That is a complement of given function. First step is dual. Second step is complementing each literal. Right. Now, one more. Let me take one more. A plus B bar and with C bar plus D E bar. If this is given function, what is complement of function using De Morgan's principle? What is the first step? Writing dual. For writing dual, what do? Priority goes to brackets or parenthesis. Logical or logical and also parenthesis there. Priority goes to brackets or parenthesis. Coming to brackets or parenthesis, in which we have again logical or logical and. In which again we have logical or logical and. Priority goes to logical and. After getting into parenthesis, once again we are observing two functions in that. What is logical or logical and. So while writing dual of this brackets or expression in the parenthesis, again we need to apply the priority with respect to same priority order. So getting to the parenthesis or getting into the parenthesis, in that again we have logical or logical and. Priority goes to logical and then logical or. So D and E bar, D plus E bar. Writing dual. This term is logical odd with C bar. This term must be logical and with the C bar. This is dual of expression which is there in the parenthesis or brackets. Am I right? This is dual of expression which is there in the parenthesis. Now, this is logical and with V bar. That means V bar plus or logical or. So, this term dual is this. This term is logical and with B bar. This term must be logical or with B bar. Yes. This entire term is logical odd with A. This entire term must be logical and with A. Right. That is a dual of given function. Dual of given function. What is second step? Complementing each literal. A bar and with B plus C and with B bar plus E. D bar plus E. Writing dual, then complementing each literal is giving complement of a function. Giving complement of a function. Now, if I say function is like this, A, B bar, logical or with C bar D. A, B bar, logical or with C bar D. Then, first step is what? Writing dual. Writing dual. In the given function, what we have? Logical or logical and functions. Priority must be given to logical and. Again, we have two logical ands. Which one should be given priority? As they are at same level, then it is equal priority. Remember this also. There may be expression multiple terms. Then in that you have logical or logical and. So priority goes to logical and. We have two logical and functions. They are at same level. There is no other hierarchical level. It is there in the parenthesis or hierarchical level. Then we go to the right, inner parenthesis or highest priority goes to lower hierarchy. But in this, these two logical ands are at same level. Then they must be given equal priority. What is that? A and B bar dual is A plus B bar. C bar and D dual is C bar plus D. These two are logical ANDed because we have logical OR here. Be clear. Replacing dual of this, these two are logical odd in this, must be logical ANDed. That is first step. Second step, what is it here? A bar plus B, complementing each literal. C plus E bar. plus theta. So same functions are at same levels, then equal priority, then equal priority. That's the way we can apply De Morgan's principle to get complement of a function. To get complement of a function. Moving to next slide. In this, what we have learned in this slide, how to apply De Morgan's principle to get complement of a function using two steps. So irrespective of number of hierarchical levels, the complement we can get in two steps. One is writing dual, second step is complementing each letter. Arshita, wait. Right. Step by step we need to do. Sivalila. Step by step. Yeah, Dinesh Roy, you are asking about this slide, right? Now, we need to understand some more terminology of a function. Some more terminology of a function. Right. So, we need to understand some more terminology of a Boolean function, which we use frequently in our discussions. What is the terminology? Let us see. Boolean algebra. About Boolean expression, we need to learn some more terminology. Let us see what is the terminology we need to learn. First, let me define a function on input variables a, b, c. The function we say f of a comma b comma c. F of a comma b comma c. So what we are saying here, a function is defined on input variables a, b, c. Give me 2 minutes. Right. Yes. What I've been talking? ABC are input variables. It is defined a function on ABC variables. The function we are saying that f of a comma b comma c. F of a comma b comma c. ABC are input variables. I'm defining a function f of a comma b comma c. When we have three variables of this function, how many input combinations possible? 2 power 3 combinations. When we have 4 variables, 2 power 4, 16 combinations. When we have n variables, 2 power n input combinations possible. When we have 3 variables, it is possible to have 2 power 3 combinations. What is it here? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right. You are going to understand the terms very clearly. Focus on this. So let me define an arbitrary function or my own function. Point should be understood correctly. Let me define my own function or an arbitrary function. What do you mean by this? I'm not using any specific functionality to say output is 0 or 1. Simply, I'm considering an arbitrary function. Follow words correctly. Don't ask me why it is output is 1, why f is 0. So, there is no reason, there is no specific function here. I am considering an arbitrary function. Simply, for some input combination, the output is 1, for the remaining combination, output is 0. An arbitrary function I am considering. So ABC, all possibilities have written. I am defining my own function like this. What is it here? 1, 0, 0, 1, 0, 1, 1, 1. This is a function. Don't try to fix any function here. Simply, I considered some input combination output is 1, the remaining input combinations output is 0. Before writing Boolean expression of this function, let us give input combination numbers. Let us give input combination numbers. While giving input combination numbers, the important thing you need to observe is order of the input variables. What do you mean by this? While defining function, f of a comma b comma c is specified. That means a should be considered MSB, c should be considered as LSB. If function is defined f of CBA, then C becomes MSB, A becomes LSB. If I define a function f of BCA, then B becomes MSB, A becomes LSB. Depending on the order of the variables specified in the function, you need to follow the same order to give decimal equivalents of binary vectors to say these are input combination numbers. Instead of saying always 0, 0, 0, 0, 0, 0, 0, decimal equivalent is what? 0. So combination number 0 I can say. Instead of saying that combination is 0, 0, 0, I say combination number 0. Instead of saying that 1, 1, 0 combination, I say combination number 6. So that's what we are using. How we can use these numbers also, we are going to see until that. Hold on. So once again, what is it here? Before writing Boolean expression of this function, let us write input combination numbers in the order variable specified. As variable specified, f of a comma b comma c, a is MSB, c is LSB. A is MSB, c is LSB. Right? Why? What is the reason of this? What is the reason for this is important thing is while specifying inputs, they are using one order. While expecting output, they are expecting another order. So with respect to order of the input variables, it is given numbers. With the same variables order, if you are completing the function, you are getting an expression, you can say input combination numbers in that function. But options are given with default order, options are given with correct order they are expecting. Then you need to change the variables order to say input combination numbers the way they are expecting. Point should be understood correctly. We are preparing for competitive exam. Every important suggestion is useful. So I say always, instead of observing after coming out of exam hall, after completing the exam, when you go through the questions, there you might have observed what mistake you have done. Then what do you say? Right? So, no, you should not do that. So, being my students, I don't expect that you are going to do the mistakes. So that is the reason I've been suggesting this. So follow each and every suggestion correctly. And where there is a possibility for doing mistakes, mostly I've been giving that possibilities. And still, if you are finding mistakes or if you are finding mistakes in your analysis, that is specifically for you, right? So you need to rectify those. I am giving common mistakes, and you need to find your own mistakes. And if you forward those mistakes to me, I may be enhancing my way of discussion by adding these mistakes also next time. That's what I've been doing. In my experience, I've been doing that only. When students have been approaching me, they have been mentioning, sir, I've done like this. What is the mistake? That's the way people have been asking. That's the way I've been observing where students are doing mistakes. Once I learn the subject, I won't do the mistake. While learning the subject, you may be doing mistakes. And while answering questions in the exam, competitive exams, in that hurriness, there is a possibility for doing mistakes. If you are controlling that, there is a possibility for winning this race with ACE coaching. Right? So listen carefully. Every point I've been mentioning, don't take it easy. Right? So every point is important. Every discussion is important. Looks like a simple, easy, but in that itself, there is a possibility for doing mistakes because they are framing questions in easy area where there is a possibility for doing mistakes. Confirming that, especially in these years. Concept is same, but they are framing questions differently where there is a possibility for doing mistakes. They are checking our observability, whether we are observing what is given or not. Please understand my words correctly. Future aspirants or future rankers have been talking. So you must get a good rank. The reason I'm suggesting, right? Fine. Once again, what I mentioned, I have defined an arbitrary function. I think no one is getting doubt why output is 1 or 0. There is no specific reason. You can write your own function also. I'm writing an arbitrary function. You can change these ones and zeros also. Some combination I'm giving output is 1, some other combination I'm giving 0. An arbitrary function I've specified. And after that, before writing expression, what I mentioned, specify input combination numbers. While writing that input combination numbers, what I mentioned, you should follow the order specified. Where order will be specified? In the function. Where it is specified f of a comma b comma c, then a should be considered MSB, c should be considered LSB. If the function is specified f of CBA, then c is MSB, a is LSB. If it is f of BCA, then b is MSB, a is LSB. For this, what is the order of the variable specified? A, B, C. A is MSB, C is LSB. With that variables order, for these binary vectors, let us give input combination numbers which are decimal equivalents of these binary vectors in the order specified. So 0, 0, 0. Decimal equivalent is what? 0. 0, 0, 1. It is 1. 0, 1, 0. 2. 0, 1, 1. 3. 1, 0, 0. 4. 1, 0, 1. 5. 1, 1, 0. 6. 1, 1, 1. 7. Right? 1, 1, 1. It is 7. Now, let me write Boolean expression for this function. So f of a comma b comma c is 1. Let us write expression for f of a comma b comma c to be 1. f of a comma b comma c is 1 when a equal to 0, b equal to 0 and c equal to 0. Or a equals to 0, b equals to 1 and c equals to 1. Or a equals to 1 and b equal to 0 and c equals to 1. Or a equals to 1 and b equals to 1 and c equal to 0. Or a equals to 1 and b equals to 1 and c equals to 1. F of a comma b comma c is 1 when a equal to 0 and b equal to 0 and c equal to 0. Or a equal to 0 and b equals to 1 and c equals to 1. Or a equals to 1 and b equal to 0 and c equals to 1. Or a equals to 1 and b equals to 1 and c equal to 0. Or a equals to 1 and b equals to 1 and c equals to 1. Whatever I said in words, let me express in expression. F of a comma b comma c is 1. F of a comma b comma c is 1 when a equal to 0 and b equal to 0 and c equal to 0. What I can write? A equal to 0 and b equal to 0 and c equal to 0. Or a equal to 0 and b equals to 1 and c equals to 1. What is here? A equal to 0 and b equals to 1 and c equals to 1. Then what is that? A equal to 0 and b equals to 1 and c equals to 1. Or what next? A equals to 1 and b equal to 0 and c equals to 1. A, b bar, c. Or what is next? When a equals to 1 and b equals to 1 and c equal to 0. A, b, c bar. Or a equals to 1 and b equals to 1 and c equals to 1. What is this here? A, B, C. A, B, C. Right? So what we have written? Expression for f of a comma b comma c to be 1. Now, this expression is called SOP. What is SOP? Sum of products. By taking products of each and every term, then we have taken summation of that. Sum of products, which is also named as a standard SOP or canonical SOP. What is this? Standard or canonical form is nothing but in each and every product term, all the input variables are available either in complementary or uncomplementary form. Right? Canonical or standard form means it is standard, it is not minimized. So each and every term is consisting of all the input variables either in complementary or uncomplementary form. Either in complementary or uncomplementary form. Then A bar, B bar, C bar is a product term. A bar, B, C is a product term. A, B bar, C is product term. A, B, C bar is product term. A, B, C is also product term. These products we have taken summation, so it is called summation of products. Also named as standard or right, canonical. Reason for this is in each and every term, all the input variables are available either in complementary or uncomplementary. These product terms are called what? Min terms of function. Min terms of function. These product terms are called min terms of function. Okay. Am I speed? Am I speed? Okay. Okay. One person mentioned as slow down. No? All that will be discussed with examples. Pawan Kumar, please wait up. Yes, there will be difference, Nagalingeshwar Rao. Is there any problem in voice? Okay, okay, okay. What type of noise you are observing? Background noise? Paper? It's not paper. Fan is there. Yes, yes. I'll come to that, Gopal Krishna. Just wait. Clear now? Everything? Yes, yes. I don't have AC in this room. The reason I'm using fan. Yes, thank you, Arpit Anand. I'll do. Yes. Okay. This expression we are naming it as what? Sum of products. Sum of products, SOP. And also, we can say it is a standard SOP or canonical SOP. This expression can be standard or canonical. The reason is to say standard or canonical in this SOP form, each and every product term must have all the input variables. Right? For example, some people are having doubt, will there be any different sum of products term or standard sum of products term? Some people have been saying that. So, AB plus A bar B plus AB bar. This is a expression, two variable function. It is what? It is what? Canonical or standard. Two variable function means in this each and every term is having two variables. That is this is canonical form. This is canonical form. Then what I can say here in this what I do in this let me take a common A. What we get here? B plus B bar plus A bar B. Then what we get here? A plus A bar B. This is also sum of products, right? This is also sum of products. But is this in canonical or standard form? No. It is also SOP, but it is not in canonical form. Some minimization is done. We are some intermediate level or minimization or final level. Such expressions cannot be standard or canonical. Understand correctly? Difference. So when can we say it is standard or canonical? in each and every term, if all the input variables are available, either in complementary or uncomplementary form. In SOP form, so in each and every product term, if we are having all the input variables either in complementary or uncomplementary form, then it is called canonical or standard form. Now, these product terms are called min terms of function. These product terms are called min terms of the function. When can we say it is min term? What is min term? Min term is a product term, but every product term is not min term of this function. If you are observing that 3 variables, 2 power 3, 8 combinations, for each and every combination you can write what is it here? Product term. A bar, B bar, C bar, A bar, B bar, C, A bar, B, C bar, so and so A, B, C. We can have 8 product terms, but every product term is not a min term of this function. So which are min terms of a function? Min term is a product term, the input combination for which function is 1 or output is 1. Once again, what is it here? What is that min term is? Every product term is not min term. Min term is a product term, correct? But every product term is not min term. So how can I say clearly about min term is? Min term is a product term, the input combination for which this function is 1. Right? Now, A bar, B bar, C bar is a min term. A bar, B, C is min term. A, B bar, C is min term. A, B, C bar is min term. A, B, C is min term. Right? Once again, these product terms are called min terms of the function. These product terms are called min terms of the function. So how can I define min term of a function? Min term is a product term, the input combination for which function is 1. Then A bar, B bar, C bar is a min term because 0, 0, 0 combination function is 1. A bar, B bar, C bar is becoming min term because for ABC 0, 0, 0 function is becoming 1. Then what I can express this is min term 0. I can say this A bar, B bar, C bar is min term 0, M0, small m 0. Small m is indicate min term. Which number? 0. 0th combination, it is min term. Plus A bar, BC is also min term. Because of which combination? 0, 1, 1, function is 1. For 0, 1, 1 combination as function is 1, so what we can say it is a M3. Because for 3 combination function is 1. This we can express it as A bar BC, we can express it as M3. Or A B bar C. So 1, 0, 1. So it is M5. Plus A B C bar 1, 1, 0. It is M6. A B C 1, 1, 1. It is M7. Right. This also can be expressed as sigma m of 0, 3, 5, 6, 7. Sigma m of 0, 3, 5, 6, 7. Summation of min terms 0, 3, 5, 6, 7. Right. So once again, what we have learned here, the expression we have written is what? SOP, and also can be named as a canonical or standard SOP because in each and every product term, all the input variables are available either in complementary or uncomplementary form. So it can be named as standard or canonical. And what is min term? All these product terms are called min terms in this expression. All these are called min terms. But how can you define min term? Min term is a product term, the input combination for which function is 1. Right? And after that, if you are observing A bar, B bar, C bar, because of 0, 0, 0 combination, this M0. A bar, B, C, because of 0, 1, 1, 3 combination. A, B bar, C, 5. A, B, C bar, 6. A, B, C, it is 7. That we are expressing it as a sigma M of 0, 3, 5, 6, 7. Let me write another expression, which is F bar of A, comma, B, comma, C. F bar of A, comma, B, comma, C. Let me write another expression, F bar of A, comma, B. Let me write that F bar column. What is F bar column? Exactly complement. 0, 1, 1, 0, 1, 0, 0, 0. I hope everyone is understanding how I'm writing F bar. Just complement of this. Now, F bar of A comma B comma C is 1 when ABC 0 0 1 F bar is 1. ABC 0 1 0 F bar is 1. ABC 1 0 0 F bar is 1. Then what we can write here? F bar of A comma B comma C equals to A bar B bar C plus A bar B C bar plus A B bar C. A B bar C bar 1 0. Observe correctly what is it here? F bar of A comma B comma C to be 1 we are writing. F bar of A comma B comma C is what? This is a column. So in this here it is 1. Which combination is that? 0 0 1 A bar B bar C. F bar is 1 for 0 1 0 A bar B C bar. F bar is 1 for ABC 1 0 0 A B bar C. Now F of A comma B comma C is equals to F bar of A comma B comma C whole bar. Then A bar B bar C plus A bar B C bar plus A B bar C bar whole bar. Correct? F equals to F bar whole bar. F bar of A comma B comma C whole bar. F bar of A comma B comma C is this complement of this. Then what we get here? A bar B bar C whole bar. Correct? Applying De Morgan's and with A bar B C bar whole bar and with A B bar C bar whole bar is equals to what we can write? A plus B plus C bar and with A plus B bar plus C and with A bar plus B plus C. Right? If you are observing, this expression is in the form of POS. Some terms are taken product. And also we can say it is standard POS and also canonical POS. Canonical POS. Once again, what is it here? Expression is in the form of product of sums. POS. POS. Right? So here we are naming it as a standard or canonical. Reason is in each and every sum term also all the variables are available either in complementary or uncomplementary form. I hope you might have understood from here. I have written F bar expression. I'm getting F from F bar. How to get that F from F bar? F bar whole bar. That's what we are writing here. And again, expanding this, we are getting this expression, which is F of A comma B comma C. So if you are observing this expression, it is in the form of a product of sums. Sum terms taken product of sums, product of sums. So here it is also named as a standard or canonical POS. Reason is each and every sum term is having all the input variables. So it can be named as a standard or canonical form. Right. See, these expressions are what? POS, product of sums. Now, these sum terms are called, what is that? Max terms. Right? These product terms are called max terms. These product terms are called, these sum terms are called max terms. We are taking product of sums, right? These sum terms are called max terms. What is max term? Sum term. But every sum term is not max term. Then what we can say? Max term is a sum term, the input combination for which function f is 0. Let me say that about f I'm talking. So these terms are called, these three terms are called max terms of this function f. When can you say it is max term? Max term is a sum term, the input combination for which function is 0. The input combination for which function f is 0. Be clear about this. Once again, what is it here? These sum terms are max terms of this function f. So how can I define max term of a function? Max term is a sum term, the input combination for which function f is 0. Right? So a plus b plus c bar is a max term because of which input combination? A means 1, b is 1, c is 0. That is 1, 1, 0. No. Be clear about this. How to find a combination number from max term? From max term. Be clear about this. What is it here? A plus b plus c bar. It is not 1, 1, 0. It is 0, 0, 1. As 0, 0, 1 combination, function f is 0. We are getting max term is a plus b plus c bar. That means while observing max term or sum term, what we need to think is if it is a 0, if it is a bar, it is 1. That means uncomplementary variable is 0, complementary variable 1. Exactly reverse for min term. What is that here? A bar, b bar, c bar means 0, 0, 0. If it is a plus b plus c, then it is 0, 0, 0 in max term. So if it is 0, uncomplementary, if it is 1, complementary, then the combination number here is the max term because of which input combination? 0, 0, 1. Be clear about this. 0 is uncomplimentary, 1 is complementary. When it is a plus b plus c bar, it is 0, 0, 1. Then what is it here? Capital M1. Max term 1. Now, a plus b bar plus c, that is 0, 1, 0. That means it is a M2. Am I right? Capital M1 product, capital M2 product. Then a bar plus b plus c means a bar means a is 1 because complementary variable. Next b means it is 0. C it is 0. That means 1, 0, 0. Then it is what? M4. M4. What is it here? A plus b plus c bar 0, 0, 1. A plus b bar plus c 1, 0, 1, 0. A bar plus b plus c 1, 0, 0. So these are max term combinations. So M1 and with M2 and with M4. This we can express it as pi m of means product of max terms 1, 2, 4. Pi m of 1, 2, 4. Right. What we have done? First we have written f bar expression. We are getting f from f bar, which is nothing but f bar whole bar. F bar whole bar. We are getting that expression for f in POS product of sums, and which we name it as the standard or canonical when we have all the input variables in each and every sum term. And these sum terms are called max terms. The max term is nothing but sum term, the input combination for which function f is 0. Then we are expressing here max term numbers. How? By observing sum term, we are writing that combination number as subscript for capital M, which are representing max term numbers. While writing that numbers, observing binary vectors with respect to sum term, in that if the variable is uncomplementary, then it is 0. If the variable is 1, complementary. For example, if it is a 0, 1, 0 combination, if function is 0, so a bar plus b plus c bar is wrong. What we need to write? A plus b bar plus c. Check it correctly. What we need to write? A plus b bar plus c. If you want to write max term directly by observing combination for which f is 0, then directly if you are writing, what is that here? For 0, 1, 0 combination, if function is 0, the maximum expression is a plus b bar plus c. 0 is uncomplementary, 1 is complementary. With that itself, we are calculating here. What is that here? A plus b plus c bar means 0, 0, 1. And a plus b bar plus c, 0, 1, 0. A bar plus b plus c, it is 1, 0, 0. Writing here M1, M2, M4. 1, 0, 0, 1. 0, 1, 0, 2. 1, 0, 0, 4. These are max terms. Then pi m of 1, 2, 4. What is pi m? Product of max terms. Product of max terms 1, 2, 4. Product of max terms 1, 2, 4. Right. So one by one, once again, what is it here? We have written SOP. We have understood what is standard canonical form. We have understood what is min term. Then we have seen how to express function f with sigma m of min term numbers. And after that, what we have done? Writing f bar, taking complement of f bar, we are getting f. Then we are getting an expression for f in product of sums, and which is also named as standard POS or canonical POS, when all the input variables are available in each and every sum term. And after that, what we are observing here? Writing max term combinations by observing variable is 0, uncomplementary, variable is 1, complementary. With that, we have written max term numbers. Then we have written, or we have expressed phi m of product of max terms, the numbers which are given 1, 2, 4. Right. After all these, let us see what is that exactly relation between SOP and POS. SOP we are writing using ones or output ones of F. POS we are writing zeros, which are max terms. SOP we are writing using min terms, which are ones. POS we are writing using max terms, the input combination for which output is 0. What can be the relation between these two? You can reply in the chat box. Manisha, if it is not in standard form, it is a normal SOP, simply SOP. Standard SOP is also an SOP. Why we are saying specifically standard? Observing all the variables are available. If all the variables are not available, normally we say that it is SOP. That's it. Manisha. Right. Inverse, complement, dual. Okay. Complements of each other. Okay. Okay. There is no specific reason to say it is min term or max term. Min, small, max. That's it. Once they have used a name by observing, writing a term, small, min, max, it is taking, right, like looking like maximum. Otherwise, no specific reason why it is min term or max term. Right? Gopalakrishna Reddy. Yes. Very good. Very good. Okay. Right. Some are answering correctly. Right. As expected, everyone is saying that SOP is complement of POS, which is wrong. Which is wrong. How can you confirm that? By substituting some combinations in both the expressions. By substituting some combinations in both the expressions, you can verify whether it is giving complementary response or same response or any other relation. Right? Right. As you expected, SOP is complement of POS. Many of you have replied with SOP is complement of POS. Whether it is correct or not, let us verify. If I substitute an input combination, observe correctly, understand correctly. If I substitute an input combination in SOP, if it is giving 1, if I substitute same combination in POS, it must be giving 0 according to your statement. See, if I substitute an input combination in SOP, if it is giving output 1, if I substitute same combination in POS, it must be giving 0 according to your statement. What is that here? SOP is complement of POS. And vice versa. And vice versa. Let us verify. Simple thing. If I substitute 0, 0, 0 combination in SOP as well as POS, observe, everyone should follow correctly. If I substitute 0, 0, 0 combination in SOP and POS, 0 bar, 0 bar, 0 bar. What is it? 1 and 1 and 1. Am I right? 1 and 1 and 1. What is this term? 1. 1 logical or with whatever it be. It may be 0, it may be 1. What do you get? 1 only. For 0, 0, 0 combination, SOP is resulting output 1. No doubt in that, right? Just substituting. Let me substitute same 0, 0, 0 combination in POS. What is it here? 0 plus 0 plus 0 bar. What is 0 bar? 1. That means this term is becoming 1. 0 plus 0 bar plus 0. What is it here? 0 plus 0 bar. 0 bar is what? 1. So 0 or 1 or 0. What we get here? Again 1. Then again here 0 bar 1 plus 0 plus 0. What I am substituting? ABC 0, 0, 0. So 0 plus 0 plus 0 bar. 0 bar is 1. This term is 1. 0 plus 0 bar plus 0. 0 bar is 1. This term is becoming 1. 0 bar plus 0 plus 0. What is it here? 1. So 1 and 1 and 1. What is the resultant? 1 only. When I am substituting 0, 0, 0 combination, SOP is giving 1, POS also giving 1 only. Let me substitute one more combination 0, 0, 1. Let me substitute one more combination 0, 0, 1 in SOP and POS. Observe correctly. 0 bar, 0 bar, 1 bar. What is 1 bar? 0. If it is 1 bar 0, this term is becoming 0. When I am substituting 0, 0, 1 combination in this SOP, 0 bar, 0 bar, 1 bar. What is 1 bar? 0. Then this is 0. Plus 0 bar, 0, 0. 0 bar is what? 1. So, but 1 and 0 and 0. This is 0. Or what is this here? 0, 0, 1. I am substituting. 0. A itself is 0. This term is becoming 0. A itself is 0. This is becoming 0. A itself is 0. This is becoming 0. Then 0, 0, 0, 0, 0. What do we get here? 0. For 0, 0, 1 combination, SOP is giving 0. What about POS? What about POS? 0 plus 0 plus 1 bar. I'm substituting 0, 0, 1 combination in POS. 0 plus 0 plus 1 bar. What is 1 bar? 0. That means 0 plus 0 plus 0. What is this here? 0. When this term is becoming 0, 0 and with this, whatever it be, it is 0. That means when I'm substituting 0, 0, 0 combination SOP and POS, both are giving 1. When I'm substituting 0, 0, 1 combination in both SOP and POS, both are giving 0. Right? Right? Then are they complements? Why do you expect complement first of all? Here you are saying it is F. Is it F bar to get complement? No. I have taken F bar and again complemented. We are getting F only. SOP, POS are not complements of each other. SOP and POS are two different expressions for same functionality. Once again, SOP and POS are not complements of each other. SOP and POS are two different expressions for same functionality. Functionality is not different. Functionality is same. They are not complements. They are not complements. SOP, POS expressions are giving same functionality. Functionally, those two are same. Functionality, there won't be any difference. They are two different expressions for same functionality. SOP, POS are two different expressions for one functionality. Then which one is correct functionally? Both are correct. Both are correct functionally. There won't be any doubt in this. There should not be any doubt. SOP expression is giving the same table F, it is satisfying. POS expression also satisfying same table which is given. Which one should I implement? Functionally, you can implement any one. And what are the other parameters we need to check? Complexity we need to check. All these you will understand after getting into K-map minimization and that hold on. At this moment, what is the clarity we need to get is these two are not different These two are giving same functionality. Why I've been stressing this much about this point is, and they have given already a number of times questions on this property, and they may be giving in coming exams also. So what they are doing is, by giving minterms in the function, the function is equal to, then options will be given in POS. When maximums are given, two options will be given in POS, two options will be given in SOP. But correct option may be in POS, correct option may be in SOP. So by expressing function using maxterms, they may be giving two options in POS, two options in SOP. As maxterms are given, some of you may be neglecting SOP expressions will be wrong. No, it may be given correct answer in SOP itself. When can we understand that? When you are understanding relation between SOP and POS. If you think that SOP is complement of POS, where is the possibility of thinking answer may be in another form, right? So you should not think these two are different. These two are same. Many of my students have been getting this confusion, or maybe having that confusion. They are getting clear after my discussions. Many, mostly students have been saying that SOP is complement of POS, because SOP is using ones, POS is using zeros. But while writing expression, there is a difference. The difference is giving functionality is same. Observe correctly. I'm not using same rules writing SOP and POS. I'm not using same rules for minterms and maxterms. Correct? There is a reason both are giving same functionality. SOP, POS, both are giving same functionality. They are not different expressions. Sorry, they are not different functions. Yes. Yes, Chakrabarti. Yes, 100%. Yes, we take Nagalingeshwara, we take. Yes. Focus on my words correctly. If you're not able to understand the words, let me know. I'll help you. I'll make you to understand the concepts correctly. So finally, what is the conclusion? SOP and POS are not different functions. SOP and POS are two different expressions for same functionality. SOP and POS are two different expressions for same functionality. Right. Let me take a small break, then we'll continue. Right. So let me take a 15 minutes break from now. We'll resume in 15 minutes. welcome back. Why people are raising hands? Ratapriya, Bharat Kumar, Raghavendra. Why are you raising your hands? I'll give you time at the end. Let me continue with my discussion. Is it audible what I'm saying? Yes. Okay. Okay. Right. I hope I'm trying to give you clarity for all your confusions. I'm trying my level best. Still, if you are having any confusions or doubts, you can ask me at the end. Wait. I'm trying to give you that clarity. So finally, what is conclusion? Functionally, what we can say in this example, for this function, sigma m of 0, 3, 5, 6, 7 is equals to pi m of 1, 2, 4. Right? Not visible. Let me change here. Final conclusion of this discussion is so those two SOP and POS are giving same functionality that we can express it as a sigma m of 0, 3, 5, 6, 7 is equals to pi m of 1, 2, 4. These two are equal, same, functionality is same, right? Those are not complements, right? So what we have learned in the Boolean basics is what is the base of Boolean algebra, three basic functions. Then what is that Boolean rules? What is the De Morgan's principle to get complement of a function? What is the min term? What is max term? What is SOP, POS? What is canonical or standard form? And what is the relation between SOP and POS? How to get complement of a function using De Morgan's principle? How to write dual? Right? These are the basic things of Boolean algebra we have studied. Right? We started with the Boolean rules. Right? Then we have seen how to get a complement of a function. What is exactly variable and literal difference? Then we have seen what is the terminology of Boolean expression, min term, max term, SOP, POS, standard forms of SOP and POS, and what is the relation between SOP and POS. That's what we have addressed Boolean basics. Advanced topics of Boolean algebra will be discussed. Hold on. Now, logic gates. What are the logic gates we have? What is the functionality of that? And all these, let us see one by one. Right? So, logic gates. Let us start with the OR gate. OR gate. So, if I say two input OR gate, right? Two inputs AB, output Y is equals to A logical OR B. Known function only. Right? Logic function already known thing. So how do you represent logic gate? What is speciality of this? Let us see one by one. AB is 0, 0, 0, 1, 1, 0, 1, 1. What can be the output Y? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. right? Here we have OR gate. A, B, Y. The symbol is this OR gate symbol. Now, one more thing we need to understand here. OR gate. Observe correctly. OR gate. If one input is 0, what can be the output? Pawan Kumar, wait. You can ask such doubts, sir. Right, and then, yes. It is not for gate exam. There is other reason to say it is gate. I'll talk it later. Right, wait. So, OR gate. OR gate, if one input is 0, what is the output? X. For OR gate, one input is 1. What is the output? 1 logical or X. It is a 1. Right? If one input is 0 for OR gate, see, output is depending on other input. Right. For OR gate, if one input is 0, output is depending on other input. That means if I change this X, it is possible to change the output. So gate output can be changed by changing this X. That means this logic gate is responding to X variations. Gate is open for X variations. As one input is 0, I'm changing other input. The changes are occurring in the output. Gate is responding to other input variations. Gate is open for other input variations. Gate is enabled for other inputs when one input is 0. This logic 0 is enabling the gate. So logic 0 is called enable input of OR gate. Try to understand terminology correctly. See, when one input is 0 for OR gate, output is depending on other input. If I'm changing this X other input, it is possible to change the gate output. That means gate is open for other input variation. Gate is enabled for other input variations. All this because of one input is 0. That logic 0 enabling the gate. So 0 is called enable input. What is it here? 0 is called enable input. Now, for this OR gate itself, if one input is 1, what is the output? Irrespective of other input, output is 1. For this OR gate, one input is 1, irrespective of other input, output is 1. That means gate is not responding to other input variation, X variations. Gate is blocking X variations. Gate is not open for X variation. Gate is disabled for X variation. And what we can say, logic 1 is disabling the gate. Logic 1 is disabling the gate. So logic 1 is called disable input of OR gate. Logic 1 is a disable input of OR gate. Understand correctly. What is it here? OR gate, one input is 0, output is depending on other input. That means 0 is enabling the gate. When OR gate connected to one input is 1, output is 1 irrespective of other input. That means other inputs are disabled. Then logic 1 is disabling the gate, logic 0 is enabling the gate. For OR gate, OR gate 0 is enable input, 1 is disable input. 1 is disable input. Logic 0 is enable input, logic 1 is disable input of OR gate. Right? So this is a OR gate functionality. First of all, what is enable and disable inputs? If you want to know, let me write. What is it here? Enable input. What can we write enable input? The input which is allowing other inputs to pass through the gate is called enable input. What is disable input? Which is not allowing, right? The input which is not allowing other inputs to pass through the gate is called disable input. Is called disable input. Enable input, disable input. Which is allowing other inputs to pass through the gate, then it is called enable. Which is not allowing, then it is called disable input. That is a difference between enable and disable. Yes, this is a OR gate symbol, which is enable and disable inputs. Now, let me implement this OR gate functionality using switches. Understand correctly? Let us implement this logical OR function using switches. First of all, let us understand what is a basic principle of switching theory. Once again, what are the basic principles of switching theory? If you are understanding, we see how it can be implemented, these functions using switching theory or switches. So what is principles of this switching theory is switches are input, bulb is output. Switches are input, bulb is output. Switch closed, input is 1, switch open, input is 0. Bulb is glowing, output is 1, bulb is not glowing, output is 0. Once again, switches are input, bulb is output. Switch closed, input is 1, switch open, input is 0. Bulb is glowing, output is 1, bulb is not glowing, output is 0. These are principles of switching theory. Using these principles of switching theory, let us implement this logical OR function. Logical OR function. Let me say here we have a supply. Let us consider two switches are in series, parallel. There is a bulb. Let me say that A, B, there is a supply. Then what we are observing in this is if A switch is closed, bulb is glowing. B switch is closed, bulb is glowing. When both the switches are closed, then also bulb is glowing. Only when both the switches are open, bulb is not glowing. समझ में आ रहा है? So what is the principles of switching theory? Switches are input, bulb is output. Switch closed, input is 1, switch open, input is 0. Bulb is glowing, output is 1, bulb is not glowing, output is 0. Then in this construction, if you are observing, A switch is closed, that means A is 1. Bulb is glowing, output is 1. B is 1. That means B switch is closed, bulb is glowing, output is 1. When both the switches are closed, that means A, B both are 1, 1. Then bulb is glowing. When both the switches are open, that means both the inputs are zeros, bulb is not glowing, output is 0. Then, yes, what we are getting here? A logical or B. A logical or B. Right? That is a two input OR gate functionality implementation using switches. If I say three input A, B, C, Y is equals to A logical or B logical or C. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Then What is output? 0, 1, 1, right? 1, 1, 1, 1, 1. Then what we are observing, output is 0 only when all the inputs are zeros. So for OR gate, output can be 0 only when all the inputs are zeros. Right? For all other input conditions, output is 1 except all zeros. Except all zeros condition, for all the input conditions, output is 1. For all zeros conditions only, output is 0. So OR gate output is 0 only when all the inputs are zeros. OR gate output is 0 only when all the inputs are zeros. Right? Yes. So what we are observing here, OR gate output is 0 only when all the inputs are zeros. I'm trying to maintain that moderate speed. If I'm speeding up unknowingly, you can interrupt me with messages. Right? Yes. If you're not understanding any concept, remember the frame number. We'll discuss at the end in doubt session. Right? This is OR gate. OR gate functionality, symbol, and enable and disable inputs of OR gate, implementation using switches, and 3-input OR gate. And what is the definition of enable and disable input? We are discussing. Now let me say that AND gate. Let me say that AND gate. A, B, output Y is equals to A and B. What is it here? 0, 0, 0, 1, 1, 0, 1, 1. What can be the output? 0, 0, 0, 1. Right? So the symbol is this. A, B, Y. AND gate symbol. Coming to enable and disable inputs. Let us see. AND gate, if one input is 0, what is the output? 0. 0 and X is 0. Then what is happening here? Disabling or enabling? Disabling. So disable input of AND gate is a 0. AND gate, if one input is 1, what is that output? X. Then what is this here? Enable. Enable input is logic 1. Enable input is logic 1. For AND gate. With respect to gate, you need to observe. It is not fixed always enable or disable input. So for OR gate, logic 0 was enabled, logic 1 was disabled. Now logic 0 is disabled, logic 1 is enabled. Now let us implement this AND gate functionality using switches. What I can do? Let us supply. Let us use 2 switches. Supply. Here we have A, B switches. What happens here? For both the switches open, bulb is not glowing. When A is closed, B is open, bulb is not glowing. When A is closed, A is open, B is closed, then also bulb is not glowing. When both the switches are closed, then bulb is glowing. When both the inputs are ones, then only output is 1. Then only output is 1. Then what is it here? Switches in series constructing logical AND operation. switches in parallel were constructing logical OR function, switches in series constructing logical AND function. A, B, C, Y is equals to A and B and C. What can we have here? 3 input. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. What can be the output? 0, 0, 0, 0, 0, 0, 0, 1. So for AND gate, any number of inputs you may be considering, output can be 1 only when all the inputs are ones. Output is 1 only when all the inputs are ones. AND gate output is 1 only when all the inputs are ones. This is about the AND gate. What we have discussed, what is the functionality of AND gate, what is the symbol, what is enable and disable inputs. Right, here AND gate implementation using switches used to implement AND function, and what is that? 3 input AND function. Similarly, next one is a NOT gate, or I say inverter. What is here? A, Y is equals to A bar, 0, 1, 1, 0. Inversion. Then symbol for this NOT gate is this. A, Y is equals to A bar. That is a NOT gate or inverter. Right. What is enable and disable input of this inverter? What is enable and disable input of this inverter? Logic 0 is enable or disable? Chakrabarti, that I do in logic families. Right. So logic 0 is enable or disable. Logic 1 is enable or disable. If you are getting these doubts, what we can say, what is enable input definition we have discussed? The input which is allowing other inputs to pass through the gate, then it is called enabled. The input which is not allowing other inputs to pass through the gate is called disabled input. Here, inverter is having only one input. Where are other inputs to pass through the gate? Functionality is of only one input. There must be other inputs to pass through the gate. No more inputs to enable or disable. Then no enable, no disable. It depends on functionality. Check correctly. So inverter is having only one input. When we have only one input, where are other inputs to pass through the gate? Where are other inputs to enable or disable? No more inputs to enable and disable. Then no enable, no disable. No enable, no disable. Right? Finally, what is the conclusion? For inverter, we don't have other inputs to pass through the gate. So it is of only one input function. Then we don't have other inputs to pass through the gate. So no enable, no disable. Then how to implement using switches? According to our discussion, what is it here? Input is 0, switch is open. Input is 1, switch is closed. Now, in this, what we are expecting, when switch is open, bulb has to glow. When switch is closed, bulb should not glow. Functionality is what? Input is 0, output is 1, input is 1, output is 0. So switch is open, bulb has to glow. Switch is closed, bulb should not glow. Then it can be implemented like this. Switch is in parallel to supply and bulb. Supply, it is A switch. What do you observe here? When A switch is closed, there exists a short across the bulb. Then current is flowing through short circuit. Current is not flowing through bulb. bulb is not glowing when switch is closed. That means when A is 1, switch is closed, bulb is not glowing, output is 0. When A is 0, that means switch is open, no alternative path for current, current is flowing to the bulb, bulb is glowing. When switch is open, bulb is glowing. When switch is closed, bulb is not glowing. When input is 1, output is 0. When input is 0, output is 1. Right? That is a inverter implementation using switch. In switch. So these are three basic gates. What is it here? And or inverter. These are three basic functions. These are three basic gates. Why? For any logic function, three basic functions are sufficient. For any digital circuit implementation, three basic logic gates are sufficient. What is it here? To implement any logic circuit, if it is available, three basic gates, logical or logical and logical inversion. If these three types of logic gates are available, we can implement any digital circuit. And the reason these three are called basic gates. Which are those? OR and inverter. These three are basic functions which are roots of Boolean algebra or basic principles of Boolean algebra. And with respect to logic gates, these three gates are called basic gates. Reason is to implement any digital circuit, the basic logic gates required is logical OR, logical and logical inversion only. So these are called basic gates. Now, let us say here one more thing, inverter followed by another inverter. Inverter followed by another one. If I say it is A, what we get here? A bar, and here it is A. Then what is this here? Buffer. We can call it as a buffer. In reality, there is no function in this. But practically, these are very important. In real IC design, we use n number of buffers. Normal buffers, clock building, right? Clock tree synthesis. In all these, we have been using buffers only. What is the advantage of these buffers? You can understand later. Not now. And with respect to our GATE and ESC course, those are not required. If it is if you are preparing for core jobs, or if you are preparing for, what is it here? Like design oriented works, then you have to know all this, and you will come to know. Once you are getting placed in any company, they will train you with all these basics. But for now, it is not required. But I can say simple thing. Buffers are introducing delay. Buffers are helping in restoring the signal. In noise environment, when logic is getting corrupted due to noise, the noise can be eliminated or signal can be restored by using repeaters, which we name it as buffers only. And all this you will understand later. So when you are understanding noise margin limits, and in that limits, when you are using logic buffers or buffers, you can see where it is restoring the signal and how it is restoring the signal also you can understand. You can understand later once you are becoming electronic engineer. When you're working on IC designs, right? So buffer is introducing delay. Buffer can be used to restore the signal. All these applications for building clocks, for making equal delay from clock port to each and every flip-flop, for not having any skew. If it is required intensely, we can make or we can introduce skew when you are observing some problems like setup violations or hold violations. In such cases, it may be required to introduce skew, which can be positive skew or negative skew. All those right? So at this moment here, we are using as a delay purpose. So we understand with respect to delay correctly. And all that, what is that here? Skew introduction or signal restoration, you are going to study in later, right? Or if you go for PG also, you are going to understand all this. Right. Finally, what is the conclusion? And or inverter are called basic gates. Basic gates. Now, let us see remaining logic gates also. What are those? NAND, NOR, XOR, XNOR. Let us start with first NOR gate. What is NOR gate? OR gate followed by NOT gate. Harish. Wait. OR gate followed by NOT gate is giving NOR gate. What is here? If A, B are inputs, Y is A plus B is OR gate functionality followed by inversion. Then what is that here? A bar dot B bar. If I say input combination 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1. So what we have here? Exactly complement of OR function. What is OR function? 0, 1, 1, 1. Now it can be 1, 0, 0, 0. Then symbol is already we observed. What is it here? OR gate followed by bubble. Bubble is indicating inversion. Bubble is indicating inversion. Consider this. So instead of writing an inverter, we are using a bubble at output side that is indicating inversion of this. Without this bubble, it is OR. Bubble, it is a not of OR, which is NOR function. Which is NOR function. So if you are observing truth table also, OR function was having 0, 1, 1, 1. Now it is exactly complement. 1, 0, 0, 0. Now for this NOR gate, if you are applying a 0 as one input, what is the output? 0 logical or with X whole bar. What is that here? X bar. Am I right? For NOR gate, one input is 0, then other input is X. 0 logical or with X whole bar. 0 logical or X is X, X bar. Right? For this NOR gate, if one input is 1, what is the output? 1 logical or X whole bar. That means 1 bar. 1 bar is what? 0. Then what we can say? Logic 0 is enabling the gate. Why? Output is depending on other input. I did not say that output must be X. I never give any such statements. What I mentioned, output must be depending on other input or other input is passing through the gate. Yes, it is passing through the gate. When one input is 0, X is passing through the gate. Output is depending on X. That means gate is responding to X variations. Then it is called enabled. If one input is 1, output is not depending on other input. What is other input here? X. So output is not depending on other input. Other input is not passing through the gate. Gate is disabled for X. So logic 1 is disabling the gate. Logic 0 is enabling the gate. What is enable input of NOR gate? Logic 0. What is disable input of NOR gate? Logic 1. Logic 1. NOR gate. Then how can we implement this NOR gate using switches? Let us see. Switches in parallel, logical OR. The parallel network is in parallel to supply and bulb is not of that. Supply A, B. So this parallel network is in parallel to supply and bulb means parallel network is giving A plus B and parallel to supply and bulb is giving not of this. Then what is it here? A plus B whole bar. Not of OR is NOR function. OR function is parallel switches. This parallel network is in parallel to supply and bulb is not of this. Right? Now, if I say 3 input A, B, C, Y is equals to A plus B plus C whole bar, which is A bar dot B bar dot C. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. What can be the output? 0, 0, 0, output is 1. 0, 0, 1, output is 0. Why? R function was having 0 all ones. Now R function will be not of this. 1 all zeros. 1 all zeros. Symbol is same. NOR gate output is 1 only when all the inputs are zeros. NOR gate output is 1 only when all the inputs are zeros. Right. That is a NOR gate. Kashyap, wait. Right. Moving to next slide. After understanding NOR gate functionality, moving to next, which is a NAND gate. Which is a NAND gate. Is nothing but AND followed by NOT. AND gate followed by NOT gate is giving NAND gate. If I say AB are inputs, Y is a AB whole bar, but we can say A bar plus B bar because A and B is AND function, not of this is NAND function. So AB whole bar, which is A bar plus B bar. 0, 0, 0, 1, 1, 0, 1, 1. Then what can be the output? 1, 1, 1, 0. Why? AND function was all zeros ones. Now NAND function is all ones 0. Now symbol is a same. AND gate followed by bubble. Bubble is indicating inversion. Right. What is enable and disable inputs of this NAND gate? Let us verify. NAND gate, if one input is 0, what is the output? 0 and X whole bar, which is 0 bar, is equals to 1. Then gate is disabled. So disable input is logic 0. Now for NAND gate itself, if one input is 1, what is the output? 1 and X whole bar, which is X bar. Now it is enabling. Which one is enabling? Logic 1 is enabling. For NAND gate, if one input is 0, output is not depending on other input X. That is the reason gate is disabled. Disabled input is logic 0. If one input is 1, output is X bar, which is complement of other input. Then gate is enabled for X. It is enabling. Any questions? Right. Now, logic 0 is disable input. Logic 1 is enable input. Let us implement this function using switches also. Then supply switches in series logical and the series connection is in parallel to supply and bulb. Supply A, B, Y is equals to A, B. Switches in series logical and the series connection is in parallel to supply and bulb, then it is not of this, not of and is NAND function. Not of and is NAND function. If I say 3 input NAND gate A, B, C, Y is equals to A, B, C whole bar, which is A bar plus B bar plus C bar. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Then what can be the output? Exactly complement of AND function. All zeros 1 AND function, all ones 0 is NAND function. all ones. Symbol is same symbol, except there are three inputs. Right. So NAND gate output is 0 only when all the inputs are ones. NAND gate output is 0 only when all the inputs are ones. Clear? So these are NOR gate and NAND gate. These NOR gates and NAND gates are having speciality. What is speciality of NOR gate and NAND gate? Universal. So NOR gate and NAND gates are having speciality, which is nothing but universal. It is universal. Right. Ankur Kashyap. Please lower the hand. Ranjita also. Right. Please wait. If you are having it out. Unknowingly, if it is pressing, just check it. Because I may be getting, keep on checking that. So, right. So these two gates, NOR gates and NAND gates are having a speciality. Manikanta. NOR gate and NAND gate are having speciality. What is speciality? Universal. What do you mean by universal? When can we say a gate is universal? That's what we need to learn. Once again, what is it here? If you're having doubt in this, let us get clarity. When can we say a gate is universal? What do you mean by universal? If it is possible to implement any logic function in universe. If it is possible to implement any logic function in universe using only the gates, then the gate is called universal. Then the gate is called universal. Try to understand point correctly. These two gates, NOR gate and NAND gate, are having speciality, which is nothing but a universal. First of all, what do you mean by universal? If it is possible to implement any logic function in universe using only the gates, point should be understood correctly. Using only the gates means if I am saying that NOR gates, using only NOR gates, it must be possible to implement any logic function. If I say NAND gates, using only NAND gates, it must be possible to implement any logic function. Then it is called universal. But in universe, we have infinite functions. In universe, we have infinite functions. Can we go with infinite functions to verify with a logic gate? No, impossible. Then what we do? Indirectly, we are proving. How? To implement any function in universe, any logic function in universe, the basic functions required is logical OR, logical AND, logical inversion. Point should be understood correctly. To implement any logic function in universe, the basic functions required is logical OR, logical AND, logical inversion. If it is possible to implement these three gates, indirectly we can say it is universal. Once again, universal gate. What is universal gate? If it is possible to implement any logic function in universe using only the gate, then it is called universal. We cannot go with infinite function in universe, but infinite functions can be implemented using three basic functions only. If these three basic functions are possible to implement using only the gates, then the gate is called universal. If it is possible to implement three basic functions, AND function, OR function, NOT function. If it is possible to implement these three, it is possible to implement any logic function in universe. Here. So let us see what is universal gate and how to prove universal gates, and how to prove this NOR and NAND. Are there any other universal gates also? You need to verify, right? So first, universal gate. If I am analyzing about NOR gates, using only NOR gates, it must be possible to implement any logic function. If I say about NAND gates, using only NAND gates, it must be possible to implement any logic function. But as we are not going with infinite functions in universe, what we are saying that indirectly we are proving. How? By implementing three basic functions, AND function, OR function, NOT function, using only the gates. What is it here? Veera Babu. And the gate is universal gate. This is what we are using. So let us prove one by one this NOR and NAND are universal. I'm moving to next slide. If it is possible to implement any logic function in universe, then the gate is called universal. Indirectly, we are proving what is it here? By implementing three basic functions and or inverter using only the gates, then the gate is called universal. Then the gate is called universal. Let us prove NOR gate and NAND gate which are universal. First, let me try with the NOR gate. What is NOR gate functionality? If AB are inputs, output Y is A plus B whole bar, which is A bar dot B bar. Which is A bar dot B bar. This is what we have. And what we need to implement, NOT gate functionality, OR gate functionality, AND gate functionality using only NOR gates. To say NOR gate is universal. Let us quickly complete that, which we know already, NOT function. How to implement NOT gate functionality? NOR gate with AB inputs, output is A plus B whole bar. If A and A are inputs, then what is the output? A plus A whole bar, which is A bar, which is A bar. NOR gate, if all the inputs are shorted, then what is the output we are getting? Inversion. So all the inputs are shorted. By connecting only one input for all, then we are getting inverse of that. Or other possibility. For this NOR gate, if one input is 0, another input is A, what we get? 0 plus A whole bar. There is nothing but A bar. It is also correct. It is also NOT gate functionality only, right? NOR gate, when all the inputs are shorted, output is complement of that one input. NOR gate, one input is 0, then output is complement of other input. Yes, inversion can be implemented using only NOR gates. I haven't used any other gates. Yes, sir. Let us implement OR gate functionality using only NOR gates. If I take NOR gate with A and B inputs, output is what? A plus B whole bar, NOR. But what is required? A plus B. Take inverse of this using NOR gates only. It is A plus B. Right? What I'm using? Only NOR gates. No other gates I'm using. Right? So NOR gate with AB inputs, output is A plus B whole bar. If I take inverse of that, we are getting A plus B. Yes, OR gate is possible. NOT gate is possible, OR gate is possible. What is remaining? AND function. Let us see. AND gate implementation using only NOR gates. AND gate implementation using only NOR gates. What is required? I need to get A and B as output and function. If you are observing NOR gate output expression, if I use AB inputs, output is A bar dot B bar. What is required? A and B. Instead of using A and B as inputs, if I use A bar and B bar as inputs, if I use A bar and B bar as inputs, A bar plus B bar whole bar, which is AB. Correct? See clearly. For NOR gate, if I use A and B as inputs, output is A plus B whole bar, which is A bar dot B bar. But required is A and B. Then if I use A bar, B bar as inputs, A bar plus B bar whole bar, which is A bar whole bar, and B bar whole bar, which is A and B. Which is A and B. That means if I use inverted inputs at NOR gate inputs, I'm getting AND function. See, NOR gate with A bar and B bar as inputs, what do we get? A bar plus B bar whole bar, which is AB. Check it correctly. A bar plus B bar whole bar means A bar whole bar and B bar whole bar, applying De Morgan. But I need to use NOR gates only. That means to get A bar and B bar also, I'm using NOR gates. Here it is A, B. What we are getting here? A bar, B bar. Then what we are getting here? A, B. Yes. And the function is also implemented. So NOT gate is possible, OR gate is possible, AND gate is possible. What else is required to say it is universal? No, nothing. Right? So NOR gate is universal. NOR gate is universal. So when we are applying that inverted inputs for NOR gate, it is giving AND function. When AB inputs are there, A bar dot B bar. When I'm using A bar, B bar as inputs, it is A and B. Right? Then let us say about a NAND gate. Right. Right. I'm assuming everyone is following my words. Are you there? Are you following? Yes. Very good. Yes, yes. Okay, okay, okay. Right, fine, 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 fine. Very good. So let us see NAND gate. Let us check the universalness of NAND gate. Universalness of NAND gate. So what is it here? NAND gate functionality, if you are writing with A and B as inputs, output is what? A and B whole bar, which is A bar plus B bar, right? Which is A bar plus B bar. Let us take one by one logic gate. Let me say that NOT gate. Let me say that NOT gate. How to implement NOT gate using only NAND gates? Yes, NAND gate. When all the inputs are shorted, what we are getting here? A and A whole bar, which is A bar. Or other possibility. For NAND gate itself, if I'm using one input is 1, other input is A, then what is that output? 1 and A whole bar, which is A bar. Then what is this? Inversion or NOT gate implementation using only NAND gates. Am I using any other logic gates? No, I'm using only NAND gates. By using NAND gates, inverter is possible. Then let me implement AND function first. NAND gate with AB inputs, resulting output is AB whole bar. Resulting output is AB whole bar. What is required for us? AB. So take inverse of this. Yes, take inverse of this. We are getting AB. We are getting AB. Using only NAND gates. There is no restriction to use only one gate. I can use any number of gates. I can use any number of gates. So I need to use only NAND gates to implement these basic functions. I can use any number of gates. There is no restriction for how many we need to use. Then NOT gate is possible, AND gate is possible. What else is required? OR function. Let us implement OR gate functionality using NAND gates only. For NAND gate, if AB are inputs, output is A bar plus B bar. For NAND gate, if AB are inputs, output is A bar plus B bar. What is required? A plus B. For that, I am using A bar, B bar as inputs. If I am using A bar, B bar as inputs, output will be A plus B. Because A bar, B bar, whole bar means A plus B. See, NAND gate with inverted inputs A bar and B bar. A bar and B bar. Output is what? A bar, B bar, whole bar, which is A plus B. But to get A bar and B bar also, I need to use only NAND gates. Yes. Use NAND gates only to get A bar and also B bar. So using only NAND gates, it is possible to implement NOT gate, AND gate, OR gate. NOT gate, AND gate, OR gate. So NAND gate is universal. NAND gate is universal. So NOR gate is universal, NAND gate is universal. Right? Yes. So in this, one more thing we need to observe. In NOR gate, if I'm using inverted inputs, it is getting AND function. NOR gate with inverted inputs is AND function. NAND gate with inverted inputs is OR function. Follow statements correctly and observe this. NOR gate with inverted inputs is AND function. NAND gate with inverted inputs is OR function. So let me write this. What is it here? NOR gate with inverted inputs functionally equal to, what is it? Equal to AND function. Now next one is what? What we have discussed? NAND gate with inverted. Bubble inputs is nothing but inverted inputs. Is resulting what? OR gate. NAND gate with inverted inputs is resulting OR gate functionality. Next, you should say this. OR gate with inverted means bubble inputs. What is the output? OR gate inputs are A bar, B bar. What is the output? A bar plus B bar. What it is? NAND. Check it correctly. OR gate with inverted inputs means OR gate with A bar, B bar inputs. Output is what? A bar plus B bar is nothing but AB whole bar. Yes, OR gate with bubble inputs or inverted inputs is resulting NAND function. Similarly, AND gate with bubbled inputs. What is the result? A bar dot B bar, which is nothing but A plus B whole bar. What it is resulting? NOR gate. NOR gate. AND gate with A bar, B bar inputs or bubbled inputs or inverted inputs. If I am applying for AND gate, resultant is what? A bar dot B bar, which is A plus B whole bar. A plus B whole bar is NOR gate. Right? NOR gate with bubbled inputs is AND function. NAND gate with bubbled inputs is OR function. OR gate with bubbled inputs is a NAND function. AND gate with bubbled inputs is NOR function. Right? See, they have been giving questions in objective exams. Mostly, I observed in ESC objective, IES objective, column A, column B match the following. In that, they are using bubbled inputs. Bubbled inputs are inverted inputs. Remember concepts correctly and observe how they can give questions also. Right? Column A, column B match the following, or they may be giving statements also. Which of the following statements are correct? Which of the following statements are false? This type of questions also we have been getting. Right? So in that statements, it may be mentioning what is this, right? Or by giving logic gate symbols also, they may be framing questions, right? So observe correctly. So NOR gate is universal, NAND gate is universal. Then if I apply bubbled inputs for these logic gates, what is the resultant also we have observed, right? Now, if I say a logic gate with P and Q inputs, output is P bar plus Q. What is this? Is it universal or not? Some other logic gate, it is my own logic gate I'm mentioning here, right? So if you have P and Q inputs, output is P bar plus Q. Is it universal? Is it universal? Yes, very good response. Okay, excellent. Ravi Teja, wait. Right. Okay, I understood from your responses. Right. See, this is a logic gate, a new logic gate. Can it be universal? No. Why? Only NAND and NOR are universal. Am I right? So can it be universal? Can it be universal? No, because we have studied only NAND and NOR are universal. Okay, forget about the statement, keep it aside. Let me try whether it is possible or not to implement three basic functions using this logic function or not. Let us verify. So in this logic gate, what we have here, if P and Q are inputs, output is P bar plus Q. In that, in place of P, let me current A. If in place of Q, let me current 0. Then what is that output? P bar plus Q is nothing but A bar plus 0. Then what is the resultant? A bar. Inversion is possible. I'm using the logic gate which is mentioned. No other gates I'm using. Using only that, I'm implementing A bar means inversion is possible. Inversion is possible. Right. Now, let me implement the OR function using the gate specified. Symbol, you can use your own symbol. You can write any arrow, ox and so and so. You can design your own gate. Is there any reason to use OR gate like that only? Standards we have been following. OR gate, when we are writing that symbol, is it giving internal circuit of that? No. Simply in standards we have been following, that is a symbol. So I'm using this logic gate symbol is like this. Okay, follow that. Now use P, Q, Let me say that A0, what we are getting here, A bar. Let me use one more gate because I have a feasibility of using n number of gates, but you need to use only the gate specified. Then again here it is P, Q is connected to B. What we get here? P bar plus Q, A bar whole bar plus B. Then what is it here? A plus B. A plus B. Correct? It is A plus B. Any doubt in that? In place of P, I'm using A bar by implementing A bar. I'm connecting A bar as P and Q is connected to B. Then P bar plus Q means A bar whole bar plus B, A plus B. Yes, OR gate is possible. AND gate. Is it possible to implement AND gate? Let us see. Let us see. A bar. Then what we get here? P bar plus Q means B bar plus A bar. B bar plus A bar is available. What is required? AB or BA. Then what should I do? Take inverse of this. A bar plus B bar whole bar, which is AB. Which is AB. Yes, the gate specified is now can be used to implement a NOT gate, OR gate, AND gate. Yes or no? Am I using any additional logic gates? No. I'm using only the gate specified. No additional gates I'm using. Then the gate specified is also universal. No doubt in that because NOT gate is possible, OR gate is possible, AND gate is possible. What else is required to say it is universal? Nothing is required. Already it is satisfying all the requirements of a universal gate. What else is required to say it is universal? Nothing is required. Yes, it is universal. So, which gate is that? I am naming it as a yes gate. Right? So I am naming it as a yes gate. Which gate is universal now? Right? Yes gate is universal. Huh. Wait, Gopal Krishna. Wait. Right. This is what I've been discussing from many years. Many years, I've been discussing this question. And you must get a doubt. From where you got this question? The first book which I mentioned, Digital Design by Wackerly, textbook. Unsolved question. By giving a logic function, prove it is universal. There they have used AB. So if a logic gate is producing output A bar plus B, prove it is universal. Even I thought same initially. What is that? Only NAND NOR are universal. Why other logic functions can be universal? This is what I thought when I saw that question first time. When I was preparing for GATE exam. When I was preparing for GATE exam, when I go through that question, then even like a simple law of insight. There is a different way, right? That we get generally. When we are confident about our studies, our statements, our concepts, then obviously when someone is saying that wrong statement, it looks like wrong, then obviously we get, right? So similar way I thought, but I took some time to understand what is the question, what is the possibility, because it is not asked whether it is universal or not. It is asked prove it is universal, means the author might have thought about a possibility of other universal gates. By thinking like that, I started solving that question. I solved, right? When I started discussing this for GATE and ESC exams, I've been discussing with different names. Right? In ACE platform, we are saying that ACE GATE, to say it is universal. Even in every batch, people used to laugh about this question. And intentionally, I used to make them to say that loudly, ACE GATE is universal. I never expected this type of questions in the GATE exam, but it was given in GATE 2014, I think. GATE EC paper, which is there in our classroom practice questions, question number 9, I think. If I'm not wrong, it is correct. Question number 9 in classroom practice questions of Boolean algebra logic gates. Which of the following logic gate is universal? After GATE exam, some of my students have messaged me or mailed me, ACE GATE is appeared in GATE exam. It is not ACE GATE, as we are in ACE, to say that, to remember, to convey that there is other logic gates which are universal possible. Not only NAND NOR which are universal, but we have other than NAND NOR, we have universal gates. To convey that, I've been saying these to remember somehow, I've been making them to remember as ACE GATE. But, in GATE exam, it is appeared. I really felt happy by seeing that question in GATE exam. Concepts is important. So the question made me to think in another way. That's what hats off to that Wackerly. Similar question is framed in GATE exam. Such questions also possible. Don't take it easy. Don't remember only statements. But the statement is wrong. The statement is correct. What is the statement? In the logic gates, only NAND NOR are universal. Right? In these logic gates, only NAND NOR are universal. Which logic gates? AND, OR, inverter, NAND, NOR, XOR, XNOR. In these, only NAND NOR are universal. I really observed this difference in understanding a statement, because till that time I was thinking only NAND NOR are universal. Even I assumed the same way what you are thinking. But once I have seen that question in Wackerly, my perception is changed about the statements in the textbooks. In these, only NAND NOR are universal. They are not wrong, they are correct. Our perception is wrong. Because in the logic gates and or inverter, NAND NOR, XOR, XNOR, in these, only NAND NOR are universal. In the logic gates we have been studying, no other universal gate. Confirm that. But in universe, only NAND NOR are universal is wrong statement. Right? See, you need to change our perception or our way we are understanding statements must be changed. That is possible when you are solving multiple questions. When you keep on solving questions, our understanding level has been changing. Even though there are next level of questions, if you are answering that questions, you are already above the list. For being in that list, you must be something specific. For that, you need to understand concepts in the next levels. For that, practicing. The only thing is practicing. Right? We are going to solve this question, which is there in our classroom practice questions soon. Hold on. Right. Now, not only this, I say one more logic gate also, which is universal. Let me say a logic gate with P and Q inputs. Output can be P bar Q or PQ bar. P bar Q or PQ bar is also universal. P bar Q or PQ bar. You can write that PQ bar also. Not a problem. Here also P bar plus Q or P plus Q bar is also not a problem. Because it is a commutative. As a commutative, you can write that P bar plus Q or P plus Q bar. Here P bar Q or PQ bar. You can use it. This is also universal. Verify. If you have any doubts, let me know. I'll help you. In this also, it is possible to implement three basic functions. Try on your own. I'm confirming it is universal. You can write your name for this, sir. I'm writing my name for this. Right. This is also universal. Prove it is universal. On your own. Try. Try on your own. Thank you, Gopal Krishnaldi. How do you know that? Okay. You are from ECRE. Okay. What type of questions you have been asking? Nagalingeshwar Rao. Any reason for that question? Yes, sir. The statement, what is statement you are expecting, Annapurni, right? That's what I mentioned, right? If it is possible to implement three basic functions, it is universal. Right? The statement about universal gate, if you are asking, yes, sir. If it is possible to implement three basic functions, it is universal. Yes. Try. I will help you if you are not able to. Tomorrow you can inform me if you are not able to solve this question, proving it is universal. Let me know. I'll help you. Right? Right. If you are understanding correctly, your perception must be changing again and again. I'll give you one more important thing. A logic circuit is given, whether it is universal or not. To prove this, what we are doing? By implementing AND or inverter, right? Other than NAND NOR, by giving a logic function, if it is asked you to implement or if it is asked you to verify whether it is universal or not, in such cases, what we are doing by implementing NOT gate, OR gate, AND gate. Three logic functions we are implementing. Three logic gates we are implementing. But it is not required. Why? See, NOT gate is possible. Either AND gate or OR gate is possible. See, NOT gate is compulsory. Either AND gate or OR gate is possible. Then we can say universal. So once you are confirming NOT gate is possible and any one of these AND gate or OR gate is possible, there itself we can confirm it is universal to save time. Right? Another way of thinking correctly. What is it here? Other than NAND NOR, any logic function is given to prove it is universal. I don't need to implement three basic gates. First thing is compulsory NOT gate. If it is possible to implement AND gate or if it is possible to implement OR gate, one of these two is sufficient to say it is universal. Why? For example, NOT gate is possible, AND gate is possible. NOT gate is possible, AND gate is possible. Then NAND gate is possible. When NAND gate is possible, it is universal. Right? Using only logic function specified, if it is possible to implement NOT gate, AND gate. NOT gate, AND gate are sufficient to say it is universal. Why? AND gate followed by NOT gate is a NAND gate which is universal. Confirmed. Other thing, NOT gate is possible, OR gate is possible. Then OR gate followed by NOT gate is NOR gate. Then also it is sufficient. Right? No need to implement the three gates. NOT gate, one of AND gate or OR gate is sufficient. Right? Indirectly. Already we are using indirect. What is that? To prove universal, indirectly we are saying that AND OR inverter is possible, sufficient. Not only this, what we are saying that AND gate and NOT gate or OR gate and NAND gate. Any one set is sufficient to say it is universal. Confirm? Right? मजा आ रहा है? Yes. Right. Let us implement a function f is equals to a and b logical or with c and d. Yes, sir. Ujjwal, please wait. Let us implement a logic function a and b logical or with c and d. A and B logical or with C and D. Let us implement this using logic gates. What I can do first, AND gate, and OR gate. Then what we can do using basic gates, I can implement AND of AB, then AND of CD, then OR of these two. This is what F is implemented. I hope everyone is clear with this. Just I'm trying to implement a logic function using basic gates first. Yes, AND gate, then OR gate. So A and B, C and D, OR of these two, A, B logical OR with C, D. Yes, it is possible. So if you are observing this logic circuit, from each input to output, how many gates are there? AND gate, OR gate, AND gate, OR gate, AND gate, OR gate, AND gate, OR gate. From each input to output, we have two gates. One is AND gate, second one is OR gate. One is AND gate, second one is OR gate. So this implementation is called a two-level implementation. In two levels, what we have? First level is AND, second level is OR. It is two-level implementation. In the two levels also, first level is AND, second level is OR. Second level is OR. Correct. Now, on this network or net, I am introducing two inverters. Will it change the function? No, because two inverters is a buffer. Buffer is not changing its functionality. If we are having X, here also we are getting X. By introducing two inverters, it won't be changing the functionality. Again, two more inverters on this net. Two more inverters on this net. It won't be changing the functionality. Now, let me push these two inverters left side, these two inverters right side. Understand correctly? These two inverters this side, these two inverters this side, I'm pushing them. Now, AND gate followed by inverter. What do we get? NAND gate. And again, AND gate followed by inverter is a NAND gate with A, B, C. So till this it is completed, right? Left side. What about remaining OR gate with inverted inputs? OR gate with inverted inputs is resulting what? NAND gate. OR gate with bubbled inputs. OR gate with bubbled inputs is NAND gate. Right? I'm using that here. So this thing can be replaced with again NAND gate. Right? See, in this what we are observing? Again, from input to output, we have two levels. Yes, two level implementation. But in two levels, what we have? NAND gates only. NAND gates only. Then what we can say it is two level NAND. Two level NAND. Right? The function, if you are observing, what is this? Sum of products. Sum of products. The function expressed is sum of products. Can be implemented using two level AND OR. The same can be implemented using two level NAND. Understand correctly? The function expressed is sum of products terms. Sum of products. That is implemented in first, it is two level AND OR. Second one, we have implemented two level NAND. SOP can be implemented using two level AND OR. The same can be implemented using two level NAND. Let me use another function. G is equals to A plus B and with C plus D. A plus B and with C plus D. Right. Let us implement this also. First, we need to implement parenthesis. Yes, OR gate. Then OR gate. Then ANDing these two. A, B, C, D. Then it is G. Right. So, what we have done? ORing AB, ORing CD, take AND of these two. Then again, what is it here? It is two level implementation because from each input to output we have two levels. First level is what? OR. Next level is what? AND. So function is POS. Right? POS expression is implemented using two levels. In that first level is OR, second level is AND. Two level OR AND implementation. Two level OR AND implementation. Now, same way we can do. By introducing two inverters on this net, two inverters on this another net. And after that, what we can do? Push these two inverters left side, these two inverters right side. Bubbles are indicating inverters. These two inverters left side, these two inverters right side. Then what is remaining? OR gate followed by inverter is a NOR gate. OR gate followed by inverter is giving NOR gate. What is remaining? AND gate with inverted inputs. AND gate with inverted inputs is equals to NOR gate. AND gate with inverted inputs is NOR gate. See, in this AND gate with two bubbled inputs, inverted inputs is again NOR. Again, this is also two levels. What is it here in two levels? We have NOR gates only. Two level NOR. Two level NOR. So conclusions of this discussion is SOP is implemented using two level AND OR. The same two level AND OR implementation can be replaced with two level NAND. Next, POS is implemented using two-level OR AND. The same two-level OR AND can be replaced with the two-level NOR. SOP is implemented using AND OR and NAND. POS is implemented using two-level OR and two-level NOR. That's what we need to understand. Two-level NOR. Okay. For today, let me wind up here. We have any questions? Let me go with your questions. Yes. Okay. Premnath. Premnath.
Hello, sir.
Yes. Yes, tell me.
Yeah.
Yes, Premnath.
In that 3F, sir.
Okay.
The next slide, sir. 4F.
Okay.
Sir, next slide.
Okay.
That literal means complement of each literal, sir. That
Literal means I can say A is literal, A bar is another literal. Literal means A is a literal, A bar is also a literal.
okay,
We
sir.
say variable, both A and A bar are only one variable. I don't need to count A and A bar separately for variables. For literals, I need to count A separately, A bar separately.
Okay, sir.
Right. Okay. Ankur Kashyap.
Yes, sir.
Yes, sir. Tell me.
Sir, in the slide number 17,
Yes, 17.
if the question is about what is the minimum number of NAND gate required for the implementation, then what to do?
That
Sir?
I'll talk in the next class.
Okay, sir.
But NAND gates, NOR gates required, I'll discuss.
So one more doubt, sir.
Yes.
In the 11 number slide,
Okay.
in the second example,
What is that?
NOR gate,
NOR gate only.
NOR gate. Second example of NOR gate.
Second example of NOR gate.
Below left, sir.
This one.
Yes, sir. Can I say X as a enable input?
So X is a variable. You need
Yes,
to
sir.
say either 0 or 1 is enable or disable.
Yes, sir.
X means again we have two possibilities. How can you say that?
Okay, sir. Got it, sir.
Right. Thank you. Sajjan Singh.
Good evening, sir.
Good evening. Very good evening.
Sir, in the sixth slide,
In sixth slide, wait a minute. Okay.
the function derived is a random function.
Whatever I said, don't ask me that. Same thing here. Yes, random function.
It means not for all.
Don't think why it is 1, why it is 0. I'm not designing any system for specific function. Don't try to fix any function for this.
Okay.
Right? That's what I said already. You will be getting the doubts why it is 1, why it is 0. Is there any reason? That reasons we can find when we are coming to combinational circuit design. So there we are going to implement the function for a given function, or we are going to implement a circuit for a given function. There we can think of functionality. Here my intention is I want to understand this terminology. For that, what function I am considering doesn't matter.
Okay, okay. Thank you, sir.
Simply arbitrary function I am considering. Yes. Pawan.
Hello, sir. Good evening, sir.
Good evening, Pawan. Tell me.
Sir, when we take a Boolean function like AB plus B bar plus AC, that A is repeating 2 times, no, sir. Then we can say that the number of literals you can
Consensus law you are
say,
talking
no,
about.
sir, or only one time A.
You are talking about consensus law?
Not consensus law, sir. I am talking about the number of literals, sir.
Yeah. What is that you are saying?
Let us say AB plus AC, sir.
Right. Then we say that it is a 4.
4. That A will be counted 2 times.
Yes, yes.
And another question is, and if in any circuit there are going to be at least one NOT gate and one AND or one AND or OR functionality, then it can be an universal circuit, right, sir?
What is that here? Once again.
If in a functionality there are involving one NOT gate and one AND or OR gate,
Any
then
one
it
of
can
them.
be a
Yes,
universal.
that can
Then
be
it can be universal.
Yes,
Okay,
yes.
thank you, sir.
Yes, yes. Sai Kumar.
Sir,
KVM Sai Kumar. Yes.
sir, you have explained that we can realize remaining gates using NAND and NOR like that, no, sir.
Mhm.
During last slide, sir, I have lost my internet connection during that time. So can you please briefly explain?
Which one? Which one?
Off, sir, slide like that, sir. I will tell, sir.
This one is right.
No, sir.
Universal.
About universal gate. This one, sir. This one, sir.
Okay, take.
Not this one, sir. Next one. Sir.
Okay.
This one, sir.
This one or this one?
This one, sir. This one, sir.
Okay. Okay. Done?
Sir. Yes, sir. Yes, sir.
Thank you.
Sir.
Yes.
Sir, can you briefly explain that, sir? One time.
See, from this only we are using NOR gate with inverted inputs is AND function, right? NOR gate
Sir.
with A bar B bar means inverted inputs AND function. NAND gate with A bar B bar means inverted inputs OR function.
Okay, sir.
NOR gate with inverted inputs is AND function. NAND gate with inverted inputs is OR function. That's what
OR function.
Then after that, the
Yes.
OR gate with inverted inputs is what? A bar plus B bar is output means AB
NAND
over
function.
NAND. AND gate with A bar B bar inputs, what is the output? A bar dot B bar, which is A plus B whole bar.
NOR function.
Yes, yes.
Oh, thank you, sir. Thank you, sir.
Thank you, thank you. Yes, Ramya.
Hello, sir.
Yes, ma'am. Tell me.
Sir, slide number 5F.
Yes. 5.
Sir, the last one, A plus B bar into C
Yes.
plus.
Yes.
Sir, could you please explain that on slide?
So here we have a AND function, OR function. Priority must be given to AND function. But here we have one AND function, here we have one AND function. Which one should be given priority? There is no priority in this because those two AND functions are at same level.
Okay, okay.
Right? Then parallelly we are replacing with duals of these two first. Then these two are OR, these two must be AND. That's it.
Okay, okay, sir. Thank you, sir. That's it.
Arun,
Hello, sir. Can you able to hear me?
yeah, tell me.
Sir, the last slide is there, no, sir. Last one.
Last one means, yes, this one, right?
Oh, yes, sir. It's something like small function given a plus b plus a plus ab plus cd. Here we can find it easily, sir. Like how many NAND gates or NOR gates, sir. But in
That I'll discuss
examination,
in the next
sometimes they are
class.
giving big functions.
That I'll discuss with the right minimum number of gates in the next class.
Okay, okay, thank you.
Param,
Sir, my doubt is about, can you explain one more time what is that enable and disable concept?
so the gate is enabled or disabled.
Yes.
Yes, wait. So gate is enabled, gate is responding to other input. When you are connecting 0, it is responding to other input or not. If it is responding to other input, enabling, so 0 is enabling the gate.
Okay.
When you're connecting 1, gate is not responding to other input. Gate is disabled or enabled? Disabled because of logic 1 input. So disable input is logic 1.
Okay. Okay.
0 is enabling the gate for other input. Point should be understood correctly. Statement,
Yes.
we need to understand. What is it here? Logic 0 enabling the gate for other inputs. Logic 1 is disabling the gate for other inputs.
Okay. Okay. Sir, the result may matter or not, sir? Means
Doesn't matter.
we are.
It may be X, it may be X1, maybe something else. Is it
Okay.
depending on X other inputs or not?
Means the other input should pass through that gate, right?
Yes. That means
Okay.
output should be depending on other inputs.
Okay. Okay.
That is called
Sir-
enabled.
Okay. Okay. Sir, can you explain with other example? Means next slide or something.
See,
Okay.
0,
Yes.
output is not depending on X, disabled. 1, output is depending on other input,
Okay.
enabled.
Sir, if we get.
Maybe getting a doubt here. See,
Yes. Yes.
0, here you are getting X bar.
Yes, sir.
Depending on X or not? X, depending.
Okay.
That's what we say enabling. Not
Okay.
depending on X. Then logic
Sir, it
one
is
disabled.
depending on X, no, sir. Means 1 plus X, X is involved there.
Involved, but what is the output?
Okay. Okay. Okay.
If I apply 0, output is 0. If I apply 1 here, output is 0 only. Is
Okay.
it changing with respect to X? No.
No, sir. Sir, one more doubt I have. Yesterday's concept, which you told about subtraction using those two's complement
One
constants.
complement.
Yeah, one's r and r minus one's complement. Sir, can we have some different concepts like addition or something?
Means what?
Sir, we took example of subtraction, right, yesterday.
So you want to add two numbers in other than decimal?
No, sir, not decimal. Yeah, okay, decimal is okay, sir.
Other than decimal, I'm saying.
No, sir,
Want to
not
add
other.
two numbers in octal?
Yes, sir.
I'll do.
Okay, and
You-
sir, can we apply different arithmetic operations like addition, multiplication?
You can do.
Okay, okay, sir. Are those questions asked in exam? Means,
Mostly we are using either binary or decimal. Because we are designing systems with the binary data.
okay, okay,
We're not
sir.
going to design the system with hexadecimal numbers. Hexadecimal for our convenience. Because if I say that C05F location,
Okay,
then instead of saying that 11000000 and so and so, I need to say 16 bits for address location, for example. Then what I'm saying that I'm converting to hexa, it is becoming easy. But
Sir-
system is not accepting whatever that information we are giving. When you are using 16 address lines, it is using 16 bits only. But we are
Okay,
writing in hexa for our convenience.
okay, okay. Sir, my question over there is, we can add, means we can do different operations with those complements like addition, subtraction now. Addition means we took yesterday's
No,
example for subtraction.
addition, we don't need to do any method separately. Direct addition.
Okay.
First.
Okay, okay, sir. Fine, sir.
Ajay, Ajay. Yes, Ajay, not audible. Ajay, are you talking? I'm not getting any voice. Manisha,
Sir,
yes,
in a logic gate, you said like the disable inputs and enable inputs, right, sir?
yes.
Like when we apply all those,
So, for example, I would like to design a circuit.
Yes,
The circuit must be enabled for logic 0 and logic 1,
yes,
disabled.
sir.
Then I can use there. You might have observed that decoder, logic 0 enable, logic 1 enable.
Yes, sir.
Right? I want to control the power to a block.
Yes, sir.
The current can be through a logic gate if I am applying.
Sir,
Or
for that,
power to a block, I want to disable. For example,
Yes.
clock gating, like we are doing that in IC design. Similarly, I want to enable the power, disable the power on a particular condition. So I have an output that may be logic 1 and logic 0. In which condition I want to enable the power for a block, in which condition I want to disable the power for the block. Because every block may not be functioning when processor is running. Then what we do? Some part must be disabled for power because we want to save the power. Unnecessarily that logic block is getting power, it keeps on dissipating because when clock is running, logic 0, logic 1, logic 0, logic 1. That means in a flip-flop, even though it is not responding to any input, even though it is not changing the output, the clock has been changing, then logic gates have been switching, then obviously power dissipation. That is the reason in some conditions, I want to disable power for entire. Then enabling power, disabling power. How can I do?
Yes, sir. Sir, for that we can also use multiplexer also, no, sir. Then like we with 2 inputs we can't handle much, right, sir? Like I
Multiplexer. See,
disabling it.
yes, ma'am. Multiplexer is combination of logic gates, right?
Yes, sir.
When a logic gate is giving same function, why do you want to use multiplexer? Where can we use multiplexer? When we have more control signals.
Yes, sir.
When we have more control signals, we can go for multiplexer. For example, we have 2 control signals. In 2 means 4 possibilities are there. For 4 possibilities, different operations are there. There we can go for multiplexer. What is multiplexer? Combination of logic gates only. Yes.
Sir, in last slide, another doubt. In last slide you gave for a universal gate we should have to use any and or if like I'm sorry, if for a universal gate there should be one and or, right, sir? Or I didn't understood,
No.
sir, that.
Not gate is compulsory.
Yes, sir.
Any one of not gate, any one of AND gate or OR gate sufficient.
Okay.
Not
Sir,
gate
in
is
an
compulsory.
Sir, in an expression like Boolean expression, there should be one AND gate and OR gate. That is enough for making it as a proving it as a universal gate.
No. Inversion is must.
No, sir, not like that. If any Boolean expression is there having 2 variables with one not and one AND gate, then it will be a universal.
Universal.
Yes, sir.
Right.
Thank you, sir.
Thank you. Vignesh.
Hello,
Vignesh.
sir, it's audible, sir.
Yeah, audible. Tell me.
Good evening, sir. Sir, in the flame side, you told about that universal gate. It is
Okay.
possible to implement those 3 and or and the inverse gate. Then we can say that is universal.
Yes.
But that slide I couldn't understand. That same slide.
This one you did not understand?
Ah, yes.
This is the logic function given. with P and Q input, output is P bar plus Q.
Okay, sir.
So in place of P and Q, I'm applying A and 0. Then what can be the output?
A bar.
A bar plus 0. That means A bar. That means A is input, A bar is output. Inversion is possible?
No, sir.
Inversion is possible or not? What we are getting output A bar, right?
A bar, sir.
What we are applying input A. What is the output
A.
we are getting? A bar.
A bar, yes, sir.
Yes, inversion is possible. Similarly, the same we are using here. Here we are getting A bar. Now A bar is connected to P, Q is connected to B. What is the output? P bar plus Q. When P Q input, P bar plus Q. But P is connected to A bar. A bar is P and again bar, P bar. Plus Q. What is Q? B. A bar whole bar is what? A plus B.
A.
Then A plus B is possible. And remaining AND function. What is it? A bar. Here we are getting B bar plus A bar. If we are taking that A bar plus B bar whole bar is AB. What is your doubt? Vignesh?
Sir. Sir, so it's possible now, sir.
It is possible. It is universal. That's
Okay.
what I mentioned. Oh, you understood it is not universal.
Yes, sir.
No. It is universal. So generally, we think there is no other universal gate, but there are other universal gate. I'm confirming. Don't get
Okay,
confusion. It is universal. The gate which is specified is universal.
Okay, sir. Okay.
Okay.
Thank you.
Thank you. Ravi Teja.
Hello, good evening, sir.
Good evening. Good evening.
Sir, in the 7F, sir, slide.
Okay. 7F. Okay.
7F. So before that, sir, 6F.
Okay.
Sir, in that F bar of A comma B comma C, sir, in that expression,
Okay.
can I write like that in the product of sums? Is it possible?
You want to write F bar POS.
Yes, sir, POS.
F bar POS means, so we need to write F, then F, take complement of this, we are getting POS of F bar. F
Okay.
is this. I can take F bar. F bar means, so complement of this. Then we are getting this expression. What is this expression? POS form of F bar.
F bar.
Right?
Okay.
F is written, we are taking complement of that. Yeah, F is written in SOP. I want to get F bar, then take complement of this. Then it is giving POS form of F bar.
Then I can take this summation of M of that A bar, B bar, C, like that, sir.
You are talking about F bar function means F bar is sigma M of 1 to 4. F bar is sigma M of 1 to 4.
Yes, sir.
F bar.
Okay.
Right?
Okay, sir. Thank you, sir.
Manisha.
Sir, in ERPQs, I have a doubt. Like I didn't understood somewhat in this 12th question, sir. Here in that they asked how the changes have been taken in that 6-bit register, right, sir? That is only the question, right?
Some modifications are done. Now the result is A3, A3, A2, A1, A0, 1.
Yes, sir.
Then what can be the result with N?
Means like the modification done in the 6-bit register. What were the modifications were done in 6-bit?
Forget about that. After some operations, the result is that. What is the result with respect to original number N? That is the question.
Sir,
Forget about what operations are performed.
Okay, sir. And here A3, A2, A1 and A0, which is there, no, sir. That is N, right?
That is N.
Okay, sir.
I'll discuss, if possible.
Okay.
I'm not able to frame that, slides of that classroom practice questions, because my PDF editor is not functioning. I'm not able to take a snapshot of that. There is a reason I'm not able to make slides. I'll get that soon.
Sir, like I did discussion, sir, but I have a bit doubt that that the assumption which I am doing is that true or not. Like that, I have a doubt.
Very
So that
simple question. In 2 steps, I'll show you that.
okay.
Don't need to worry. I can make that very lengthy explanation. I can make it simple also.
Yes.
Wait. Yes. If you keep on thinking that you may be getting doubt before I discuss, right?
Yes, sir.
That gives very much happiness. If you are carrying that question in your mind, if you are
Yes.
getting your own idea, you are getting answer confidently, then gives what we can say happiness.
Yes, sir.
Instead of getting answer from me, if you are able to solve on your own, you feel very much happy, right?
Yes.
But I suggest you before I solve, please try on your own. I will solve.
Yes, sir. I solved it, sir, but the way I did is
Then hold
yes.
on. You are still having a doubt? Then hold on.
No, sir. Just I have a doubt that as if the thing which I'm thinking is true or not. Like that, I just asked you.
Okay. I'll let you know. I'll let you know.
Yes, sir.
Right. So you messaged me?
Yes,
That
sir.
question?
It's me only.
Okay.
Yes, sir.
Okay. I told you, right? I'll discuss in the class.
Yes, sir.
Right. I'll discuss all the questions. Over.
Okay.
Chandu Srinivas. Chandu Srinivasa Manikanta Subramani.
Sir,
Sir.
audible?
Hello.
Sir, am I audible?
Some
Sir?
disturbance is there. Some disturbance is there.
1 second, sir. Sir, in this slide,
Yes.
we have ABC values of 0, sir.
ABC values?
Hello?
Yeah. Tell me. ABC?
0. Sir, 0, 0, 0. How
Yes.
would we get 1 in F value? Ah, yes, sir. First one, 0 value.
That's what I
How
told
would
you.
we?
Already one of your friend has already asked. Then I said, no need to worry about why we are getting 0. Why we are getting 1, why we are getting 0. No need to worry. Now I'm not designing any specific function. Simply
Okay.
blindly I followed. I've given ones and zeros. That's it. No reason why it is 1, why it is 0. Don't worry about
Okay,
functionality.
sir.
Right.
Okay, sir. Okay. And moreover, from the last side, second slide, sir.
Okay.
Sir, here we are using the universal gates for getting a problem, sir. I didn't clear on it. That's
Actually, instead of NAND and NOR, they are giving some logic function.
Okay.
So is that logic function universal or not? We need to verify.
Okay, sir.
Right.
And you are giving a problem, right, sir?
Yeah, I have given.
Yes, sir. What to do on it for
Similarly, you have to prove it is possible to implement 3 basic functions.
Okay.
The way I have done for this also you need to do that.
Okay, sir. Okay.
Right.
Thank you, sir. Thank you.
Rohit Rajendra.
Good evening, sir.
Good evening. Very good evening.
Yes, sir. In this framework, yes, sir.
Okay.
Is this gate is there or functionality, sir? This was function. This question.
What is the difference between a function and a gate?
Yes, sir.
There won't be any difference, right? I can design my own logic gates.
Okay, sir.
Right.
Sir, the second problem can be solved using that duality property, na, sir, or theorem. Dual.
What duality means a function must be there. So LHS and RHS that is proved already.
Sir, means this first problem is proved, na, sir. Then we can directly.
There is a LHS and RHS is a function, right?
Sir.
There is an equation. It is not equation. It is one function to another function.
Sir. Sir, means by dual that property, these both LHS and RHS are equal.
A function is true, dual of that function is true.
Okay, sir.
Right?
Okay, sir.
right? Equations tally, you can verify,
sir.
right? But we are talking about universal gate. So
Okay, sir.
I did not say that one function is universal, then dual of that function is also universal. Did I say that? No.
Sir, is that not correct, sir? Means
No.
one function is universal, then dual of this that equation is not universal, sir.
May not be.
Oh,
May not be.
how, sir? Means not getting.
We'll
Sir.
see. We'll see. I'll let you know. I'll check it about this.
Okay, sir. Okay, sir. Thank you.
Anyone else having doubts? Can I assume no one is having doubt? Okay, Akash.
Hello, sir.
Yes.
Sir, in this slide, you have taken to prove A as the universal gate. One input is A and other is 0. 0 as it. Can we take 1 instead of 0?
Why do you want to take 1? It is not satisfying to get A bar, right?
No, sir. Not in that. In the next question which you have given.
That you try, please.
I have tried, sir.
Yeah,
That's
you are
why.
right. You are right.
Okay, sir. Okay, sir. Thank you.
Very good. So, if you don't have doubts, okay. Oh. If you don't have any doubts, see you tomorrow. Manisha.
Sir, here in like this, we are proving that like the in sir in 16th frame, in A's gate we have proved that A and 0 to be an NOT gate, right, sir?
Yes.
Sir, there at A and 1 we can take A and 1 also, no, sir?
You can take.
Okay.
You can take. That's what idea.
Yes, sir.
Yes, yes. Done?
Okay, sir. Thank you.
Right, right. Arun Revant, are you there? I will discuss such questions tomorrow. Sai Pratyush.
Hello, sir.
Yes.
Good evening, sir.
Very good evening.
In the question, if they give us SOP
Mm-hmm.
and ask us to represent the same thing in POS,
That I'll do.
Oh.
Because that exercise we can do after getting into KMAP.
Okay, sir.
I'll show you that. Because once we are getting minterms, what is the minterms of other function? What is a POS? How can I write? All those I'll explain.
Okay, sir. Thank you, sir.
Thank you. Right. See you tomorrow, everyone.